Hello there and welcome to Science for Sleep, the little corner of the internet where curiosity slows down and science takes its time. Tonight we're not watching clocks or chasing seconds. Instead, we're lifting our gaze just a little higher, up into the night sky, into that pale, milky streak that has fascinated people for as long as eyes have opened under the stars. You've seen it in photographs, maybe from space telescopes or long exposure shots. But perhaps you've also seen it with your own eyes, stretching across a dark countryside or a mountain sky, a gentle band of light too faint for city streets to allow. That is the Milky Way, our home galaxy, the vast collection of stars and dust and invisible matter that holds us together. But how big is it really? That's the journey we'll wander through tonight. Before we dive into the spirals and distances, let me ask you something simple. Where are you listening from this evening? And what do the stars look like where you are? For some, they are crisp pinpricks in a dry desert night. For others, they are blurry behind city haze, or maybe not visible at all, hidden by neon glow. Yet no matter how clear or hidden, you are inside the Milky Way. You can't step outside of it to get a full view. You can only look outward and piece together its story from where you sit. It's like trying to imagine the whole of your neighbourhood while standing in one of its streets. You see a few houses, a few trees, maybe the end of the block, but the total picture requires patience, inference, and a bit of imagination. If you find this exploration soothing, or if the slow pace of science spoken gently helps you unwind, I'd be grateful if you considered giving this video a like, maybe even subscribing. It helps this quiet corner reach others who could use a calm companion for their thoughts. And if you're already here often, thank you for being part of this little journey. Now take a slow breath, loosen your shoulders, and allow your mind to stretch a bit further than usual. Because while the Milky Way is our familiar galactic address, it is also incomprehensibly vast, stitched with mysteries, and the perfect thing to think about while drifting toward rest. Imagine holding a map that includes everything you know. Your street, your town, your country, the entire Earth, even the solar system. Now imagine zooming that map outward until every star you see in the sky is included. That's the Milky Way. But even this description barely scratches at its true size, because the numbers involved are so large that our everyday measurements fall apart almost immediately. When we ask how big the Milky Way is, we have to remember that we are trapped inside of it. If you've ever tried to measure the size of your own house while blindfolded, you might get a sense of the challenge. You'd touch a wall, count steps, feel around corners, but you would never see the entire shape at once. Astronomers face the same challenge with our galaxy. They cannot step outside of it to take a photograph. Instead, they measure light, map star positions, and build models, slowly sketching a structure so enormous that even the speed of light, the fastest thing in the universe, needs more than 100,000 years just to cross it from one end to the other. 100,000 light years. That's the common figure given for the diameter of the Milky Way. But what does that mean? A light year is not a unit of time, but a unit of distance, the length that light travels in 1 year. Light moves at nearly 300,000 kilometers per second, faster than anything we can imagine in daily life. In a single second, a beam of light could circle the Earth more than 7 times. Multiply that by 60 for a minute, by 60 again for an hour, then by 24 for a day, then by 365 for a year. You end up with a number so large it's better left written out. Almost 10 trillion kilometers. That's a single light year. Now stretch that by 100,000. That's the Milky Way's width. Numbers like this stop feeling like numbers. They turn into abstractions, but they are real. Picture the Sun. Now imagine the nearest star, Proxima Centauri, about 4.62 light-years away. To travel that distance with today's fastest spacecraft would take tens of thousands of years. That's the tiny scale of just our local neighbourhood. Now consider multiplying that distance not by 2, not by 10, but by 25,000. That gets you to the galactic centre from where we are. Multiply it by more than twice that, and you reach the other side of the galaxy. It's not simply big, it's overwhelming. And yet, within this enormous span, stars orbit smoothly, gases swirl, and invisible dark matter keeps everything bound together in a cosmic dance. Of course, when we talk about size, we're not only talking about distances across, we're also talking about what fills those distances. The Milky Way contains hundreds of billions of stars. Some estimates suggest as few as 100 billion, others as many as 400 billion. And stars are not the only residents. Planets by the trillions, nebulae glowing with fresh births of stars, clusters of older suns packed tightly, streams of dust that block and reveal, and perhaps countless forms of life waiting quietly in places we haven't yet seen. The galaxy is not an empty expanse with stars sprinkled randomly. It is structured. It has arms, a central bulge, a surrounding halo. It has motion, as every star, including our Sun, travels in an orbit around the galactic centre. Even at this very moment, the ground under your feet, your room, your body, everything you know is orbiting at nearly 828,000 kilometres per hour around that central point, though you feel none of it because everything else nearby is moving with you. It's a strange thought. You're not sitting still. You're being carried on a massive starship that is the solar system, which itself is circling the Milky Way like a small boat in an enormous harbour. And yet to you, it feels calm, quiet, steady. Perhaps that's part of the magic of thinking about the galaxy at bedtime. It reminds you that your worries, the schedules and alarms of daily life are nestled inside something incomprehensibly bigger, steady and ancient beyond any human time scale. But our attempts to measure its size are not just curiosities. They have stories, experiments, clever tricks. Astronomers of past centuries had no way to know what the Milky Way was. To the naked eye, it looked like a faint glowing path across the heavens. Was it a cloud? Was it the edge of the universe? Ancient cultures had myths about spilled milk, crushed stars, the pathway of gods. The name Milky Way itself comes from one of those myths. Imagining milk spilled across the heavens. Only with telescopes did we realise that the glow was made of countless stars too faint to see individually. Tonight, we'll slowly move from those first impressions, through the discovery of our position within the galaxy, to the dizzying numbers that describe its true expanse. We'll talk about its spiral arms, the strange invisible matter that makes it heavier than it appears, the black hole at its heart, the companions that circle it, and even the distant future when it will collide with another great galaxy. But for now, in this opening moment, the important thing is simply to feel the scale. The Milky Way is our home, yes, but it is a home so large that no single human being will ever traverse it, no spacecraft will cross it in our lifetimes, no light we send will reach its far edges for thousands of generations, and that's where the wonder begins. Because to ask, how big is the Milky Way really, is not to get a single neat answer. It is to unfold layer after layer of measurement, inference and awe. One number might describe its diameter, another might describe the mass of its stars, another might include the invisible halo of dark matter that stretches even farther. Each answer is true, and yet each one leaves you with a sense that the galaxy is always just beyond full comprehension. As you let that thought drift in your mind, remember this. The faint ribbon of light you may have seen in the night sky, that gentle band often mistaken for a cloud, is nothing less than the cross-section of an entire galaxy, seen from the inside. It's the glow of billions of stars blending together, all of them part of a system so vast that calling it big feels almost like a joke. The sky has always been with us. Long before telescopes, long before clocks, before written words even, people tilted their heads back and wondered about the faint smear of light that stretched across the night. Imagine yourself thousands of years ago, sitting by a fire at the edge of a dark plain, the only light coming from flames and stars. There are no cities, no electric lamps, no car headlights, nothing to dim the heavens. What would have filled your vision is a sky crowded with points of light. More stars than most of us have ever seen in our entire lives, and slicing across them all, a glowing river that seemed too wide and too soft to be made of individual stars. That was the Milky Way, though of course no one called it that yet. It was simply there, a celestial mystery painted above every culture that ever looked up. When you see it in that way, far from artificial light, it becomes impossible to ignore. It is not faint or subtle. It arcs across the heavens like a glowing backbone, sometimes hazy, sometimes sharp, depending on where you stand on Earth. For many ancient observers, this sight was more than just beautiful. It begged for explanation. Why should the sky have this streak, unlike anything else in nature? Clouds move, the moon waxes and wanes, planets wander slowly. But this river of light is fixed, permanent, stretching the same way across the seasons. It seemed eternal, and so it became wrapped in myth and story. The Greeks imagined milk spilled from the breast of a goddess, giving the Milky Way its familiar name in Western languages. In China, the band of light became a river, the Silver River, with legends of lovers separated across its width who could only meet once a year. In South Africa, some traditions called it the backbone of night, a structural element of the heavens themselves. Indigenous Australians wove their own stories, often describing it as the smoke of fires or as pathways of ancestral beings. Each culture looked up, saw the same soft glow, and found meaning within it. What's striking is that these stories all recognise the Milky Way as something special, not just another collection of stars. To eyes without optical help, the band doesn't reveal itself as countless suns. It looks continuous, smooth, a mist. Some compared it to spilled flour, others to a road, still others to a scar across the sky. The way people interpreted it depended on their environment. For agricultural societies, it might have guided planting times or served as a calendar. For nomadic groups, it might have provided orientation, a permanent compass in the night. Whatever the function, it became a constant companion. Consider the psychological effect of seeing it every clear night. Today, most of us rarely see more than a dozen bright stars from our neighbourhoods. Streetlights wash out the subtle glow. But for early humans, the Milky Way was unavoidable. It was woven into their concept of reality. The sky wasn't empty. It was alive, filled with light and mystery. You might fall asleep under it, night after night, with that glowing streak above, always present, always patient. It would shape your dreams, your sense of direction, your myths about creation. The first attempts to explain it in natural terms came much later. Aristotle, writing in the 4th century BCE, thought it was a phenomenon of Earth's atmosphere, a sort of glowing exhalation caused by the burning of vapours in the upper air. He imagined it like a kind of weather effect, high above but still local. This idea lasted for centuries, accepted without question because there was no way to test it. After all, who could climb into the sky to see? The best anyone could do was look carefully and describe. It wasn't until telescopes arrived in the early 17th century that the mystery began to unravel. But before we get there, it's worth pausing to think about just how long the Milky Way was considered unknowable. For thousands upon thousands of years, it was a mystery without answer. And maybe that's part of its power. It forced people to think beyond themselves, to accept that there are things larger, stranger, and more permanent than daily life. The steady glow wasn't threatening, but it was undeniable. It wasn't like a storm you could wait out. It was always there. One of the earliest systematic sky watchers was Hipparchus of Nicaea in the 2nd century BCE. He catalogued stars, tracked their positions, and laid groundwork for future astronomy. Though he didn't solve the Milky Way's nature, he helped frame it as something worth measuring, not just admiring. Later, Ptolemy in the 2nd century CE, famous for his geocentric model of the universe, also described the Milky Way, though again in terms of atmospheric effects. The idea that it was distant, made of stars, was not yet considered. Now think of the perspective of someone in medieval Europe or Asia, still seeing the Milky Way every night but interpreting it through inherited stories. You're a farmer, perhaps, or a traveller, looking up after a long day's work. To you, the band of light might mark seasons. It might remind you of stories told by elders, of gods, spirits, or animals placed in the sky. You may never question what it is physically. Why would you? It has no immediate consequence for planting crops or finding shelter, and yet it surrounds you, silently shaping your imagination. That quiet influence on human thought is easy to underestimate. The Milky Way inspired art, poetry, and philosophy long before it was understood scientifically. Dante Alighieri, writing in the 13th century, described it as a visible effect of stars crowded together. That was closer to the truth, though still speculative. Others wondered if it was some kind of seam in the sky, a boundary between realms. Theories varied, but all shared one thing: recognition that it was unique. Fast forward to the Renaissance, when curiosity about the natural world was rekindled, and instruments began to improve. With simple lenses, people tried to look more closely at stars, the moon, the planets. Then, in 1609, Galileo Galilei turned his telescope to the sky and changed everything. When he pointed it at the Milky Way, he saw what no one had seen before. Countless faint stars packed so tightly that the eye could not distinguish them individually. The smooth glow was not a cloud. It was a collection of suns. The mystery that had hovered over humanity for millennia began to give way to observation. Imagine Galileo looking through his crude but powerful instrument, realizing that what seemed like mist was in fact a multitude. It must have been staggering. He described the Milky Way as a congeries, a collection of innumerable stars. Suddenly, the band of light wasn't a singular thing, but a vast system. It suggested that the universe was bigger, busier, and more crowded than anyone had dared imagine. This was not just philosophy. This was evidence, visible through glass. From that moment, the Milky Way became not only a cultural symbol, but a scientific object. Astronomers began to ask new questions. If it is made of stars, how many? How far do they stretch? Are they scattered evenly, or arranged in a structure? The problem, of course, was that humans were still stuck inside of it. Measuring something from within is always difficult. If you're sitting in a dense forest, you see trees around you, but not the full shape of the forest. So too with stars. Even so, Galileo's discovery lit a path that would eventually lead to the modern concept of galaxies. But before we jump forward in time, it's helpful to linger on that turning point. For the first time, the Milky Way shifted from myth into science, from metaphor into measurement. It didn't lose its wonder. If anything, it became more awe-inspiring. To think that what looked like a gentle brushstroke across the heavens was actually billions of suns was almost too much to take in. It still is. Today, with our advanced telescopes, space observatories and digital sensors, we can map the Milky Way in incredible detail. But in many ways, the experience of seeing it hasn't changed. If you find yourself on a dark night in a place far from city lights, the sight can still stop you in your tracks. It's humbling to know that every shimmer, every glow, is part of a structure that contains us. The ancient people who named it and told stories about it may not have had the details right, but they captured the essence of what we still feel, that it is vast, mysterious, and meaningful. So, when we ask how we first noticed the Milky Way, the answer is simple. We always noticed it. It was there in every night sky, shaping imagination and story, long before science gave it definition. From goddess milk to celestial rivers, from poetic metaphors to Galileo's first telescope, it has been both a canvas for human thought and a clue to something far larger than ourselves. Long before telescopes and observatories, before charts and satellites, people tried to make sense of the night sky with the only tools available: their eyes, their memory, and their imagination. To us, with apps that can identify constellations in seconds and digital images that reveal thousands of stars in a single snapshot, it might seem impossible to imagine doing astronomy with nothing but vision. Yet for most of human history, that was exactly what was done. The stars were observed carefully, compared across seasons, counted, catalogued, and woven into systems of meaning. When you stand under a very dark sky, one untouched by artificial lights, you can see thousands of stars. Estimates suggest that the average human eye can distinguish between 5,000 and 7,000 points of light under the best conditions, spread across the entire dome of the heavens. That number is far less than what truly exists, but for early observers it was already overwhelming. Imagine trying to count them one by one without any instruments, keeping track in your mind or with marks on a surface. It was a task as impossible as counting grains of sand, yet people tried. They wanted to know not just what the stars were, but how many there might be. For ancient cultures, numbers themselves were often tied to the sacred. To say that there were countless stars was to point to infinity, to something divine. The Babylonians, skilled record keepers of the sky, kept tablets with lists of stars and constellations, though they didn't attempt to count everyone. They focused on the brightest, the ones that mattered for calendars and omens. In China, detailed star charts were drawn, some of the oldest in existence, mapping out hundreds of stars and dividing them into constellations distinct from the Western ones we know today. The goal wasn't to list them all, but to create order, to make the sky navigable and meaningful. Still, the question of how many stars existed lingered. Aristotle suggested that stars were fixed lights embedded on a celestial sphere, their number finite and unchanging. Other philosophers speculated that the stars might be countless, beyond human ability to list. The Greek poet Aratus, in the 3rd century BCE, wrote of the constellations and stars visible to the naked eye, not as a scientist, but as a storyteller. His poem, The Phenomena, described the patterns of the heavens so that sailors and farmers could orient themselves. It wasn't about exact numbers, but about recognition. Knowing which stars rose in which seasons meant knowing when to plant, when to harvest, when to travel. Counting stars wasn't always literal. Sometimes it was symbolic. In many cultures, the phrase, "as many as the stars in the sky," was used to signify abundance without limit. In the Hebrew Bible, the patriarch Abraham was promised descendants as numerous as the stars. Similar metaphors appear in other traditions. To compare something to the number of stars was to place it beyond counting, into the realm of the eternal. This shows how even without precise numbers, the sky served as a reminder of scale, of human smallness, of divine largeness, and yet some did try to count directly. In the 2nd century CE, the astronomer Claudius Ptolemy compiled the Almagest, a catalogue of over 1,000 stars. It wasn't every star visible to the eye, but it was systematic, an attempt to record, organise and classify. Each star was given a position and a magnitude, an estimate of brightness. This catalogue became one of the most influential works in astronomy for centuries, passed from culture to culture, translated, expanded, but always rooted in the act of looking upward and counting what could be seen. The challenge, of course, was that the stars blur together in the densest parts of the sky. Look at the Milky Way on a dark night. You'll see that it isn't a line of distinct dots, but a glowing smear. To early eyes, this was a puzzle. Was it a cloud? Was it fire? Was it the edge of the world? Without magnification, the stars were simply too many, too close. Counting them was like trying to count drops in a waterfall. You could try, but they would always merge. Instead of fighting that, people embraced it. The uncountable nature of the stars became part of their power. Myths described them as ancestors, as spirits, as sparks from divine fires. In Polynesian navigation, stars were memorized not by number, but by position and rising time. Navigators knew the sequence of stars that would rise along their path, guiding canoes across vast oceans. This was astronomy of the most practical kind, built not on precise counts, but on living relationships with the sky. Consider also the way constellations were formed. Out of thousands of stars, people chose specific ones to connect into shapes. The Greeks saw Orion, a hunter, standing tall. The Chinese saw different patterns, like the azure dragon or the vermilion bird. In the southern hemisphere, where entirely different stars dominate, cultures created entirely different constellations. Counting wasn't about listing every point. It was about selecting, grouping, giving meaning. The uncountable backdrop became a canvas, and from it, cultures drew pictures that anchored their stories. The idea that stars might be infinite was both thrilling and unsettling. Philosophers like Democritus speculated that there might be countless worlds beyond our own, each with their own suns and perhaps their own beings. This was radical thinking, far ahead of its time. It implied that the stars were not tiny lights nearby, but distant suns themselves. If that were true, then the universe might be unimaginably large. But such ideas remained speculation, because no one could test them. The stars resisted closer inspection. They remained points of light, too far to resolve, too stubborn to reveal their secrets. This is where the Milky Way played a special role. While individual stars could be counted, at least to some extent, the Milky Way was a reminder that counting had limits. The glowing band was proof that beyond the stars we could see individually were countless more, too faint, too close together to distinguish. In that sense, it was the ultimate metaphor for the infinite. You could number 1,000 stars, but you could not number the Milky Way. It humbled observers, forced them to accept that the universe was bigger than their minds could grasp. When Galileo later turned his telescope to that glow and saw it dissolve into stars, it confirmed what myth and intuition had already suggested. The Milky Way was a collection beyond counting. But for centuries before that, its very appearance had served the same purpose. To stand under it was to feel overwhelmed, to feel part of something larger. Counting by eye was not about reaching a total. It was about reaching a realization that the sky held more than humans could ever fully tally. In daily life, this had practical consequences too. Calendars based on the stars helped regulate agriculture. Temples and monuments were aligned to rising constellations. Stories tied human events to celestial patterns. In each case, the stars were not just ornaments, but guides. They provided order in a world where seasons changed, rivers flooded, and survival depended on predicting cycles. The act of counting, even imperfectly, created a sense of control. To name a star, to record its position, was to bring a piece of the infinite into human understanding. Even today, if you go outside on a clear night and try to count stars, you'll quickly find yourself overwhelmed. Your eyes lose track, your mind loops, the sky refuses to be catalogued so simply. That feeling of futility is ancient. It is the same frustration and awe that early humans felt. And maybe that's the point. The stars are not meant to be reduced to a list. They are meant to remind us of scale. Each one is a sun, perhaps with its own planets, its own stories unfolding. To try to count them is to confront the limits of human capacity, and to accept those limits with wonder. So when we think about the ancient efforts to count the stars, we should remember that it was less about reaching a final number, and more about building a relationship with the sky. Counting was a gesture of curiosity, a way of saying, I see you, I notice you, I want to know. It was as much poetry as science, as much ritual as record-keeping, and in that sense, it was the first step on the long road that would eventually lead us to telescopes, observatories, and the staggering modern estimates of hundreds of billions of stars in the Milky Way alone. And yet the essence hasn't changed. We still look up, still wonder how many stars there are, still feel that same mix of awe and futility. The difference is that now, with our instruments, we can push the count further, deeper, seeing more than the eye ever could. But the feeling the sense of being faced with something beyond numbering that is timeless. When people first looked up at the night sky and saw that glowing streak stretching from horizon to horizon, they didn't have numbers, telescopes, or physics equations. What they had was imagination. And so, the Milky Way became a story. Not just one story, but hundreds, thousands, told in every corner of the world where human beings lived under dark skies. Each culture saw the same band of light, but what it meant, what it symbolized, how it fit into their lives, varied in ways as vast as the galaxy itself. In Greece, the name we use today was born. The Galaxias Kaiklos, meaning Milky Circle, became the origin of the term Milky Way. According to myth, it was milk from the goddess Hera, spilled across the heavens when she pulled her breast away from the infant Heracles. The drops became stars, a permanent record of divine drama. It's a strange image, but it reflects something important. People understood the Milky Way as a physical trace of powerful events. To them, the sky was not separate from daily life. It was connected, woven together with human affairs and divine action. Travel east, and the stories shift. In ancient China, the Milky Way was the Silver River. A story told of the cowherd and the weaver girl, lovers separated by the river of stars, allowed to meet only once a year when magpies formed a bridge. This tale, celebrated in the Kixi festival, gave the galaxy not just a shape but an emotional resonance. It wasn't only a stripe of light, it was a river of longing, of distance and reunion. When people looked up, they didn't just see stars, they saw a love story played out across eternity. In South Africa, the Khoisan people called it the backbone of night. They saw it as a structural feature, something holding the heavens together, like a spine. In Australia, Aboriginal groups described it as a great river, or as the smoke from ancestral fires burning in the sky. The Yolngu people of northern Australia spoke of a canoe travelling along the Milky Way, with ancestral beings guiding the cosmos. These interpretations weren't just myths told for entertainment. They were part of knowledge systems, teaching lessons, marking seasons, explaining natural cycles. For the Maya, the Milky Way was linked to the world tree, a cosmic axis that connected the underworld, the earth, and the heavens. The bright band became a celestial road, sometimes imagined as the backbone of a crocodile or the path of a canoe carrying gods. In their complex calendars and cosmology, the galaxy was central, a living presence in the order of the universe. It was not just a backdrop. It was a guide for ritual, for agriculture, for understanding existence itself. In the Andes, the Inca saw the Milky Way as a celestial river, the Mayu. It mirrored the rivers of the earth, particularly the Vilcanota, which they believed was connected directly to the Milky Way above. The movements of stars along this river were tied to seasonal cycles, rains, and crops. They even saw dark constellations within the Milky Way, shapes formed not by stars but by the dark patches of interstellar dust. Llamas, serpents, and other animals were identified in those dark regions, their rising and setting in the sky linked to agricultural rituals. The Milky Way wasn't only about light, it was about shadow too. In Native American traditions, the stories varied across tribes and regions. The Lakota Sioux spoke of the Milky Way as the spirit road, the path along which souls travelled to the afterlife. For the Cherokee, it was sometimes the trail of a dog who had stolen cornmeal, scattering it across the sky as he ran. In each version, the glowing band served as a connection, a reminder that the human world and the sky were not separate but bound together. Across the Pacific in Polynesian cultures, the Milky Way played a role in navigation. It was not just a myth, but a tool. The stars of the Milky Way marked directions, guiding canoes across thousands of miles of ocean. For them, the galaxy was a map spread above their heads, its orientation helping them find their way between islands. Imagine being at sea, no land in sight, only waves and stars. The Milky Way would stretch above like a compass, steady, reliable, telling you where you were and where you needed to go. Even in northern Europe, where clouds often covered the sky, the Milky Way became part of folklore. In some traditions, it was called the road to Valhalla, the path of souls to the realm of the gods. In others, it was thought of as a path of birds, particularly migrating ones. Observers noticed that certain birds seemed to follow the orientation of the Milky Way during migration, and so the galaxy became a celestial guide not only for humans but for animals as well. These stories reveal something important about human imagination. When faced with the unknown, we connect it to what we know. Rivers, roads, trees, animals, ancestors, love, food. These are the elements of life. When people looked at the Milky Way, they turned that endless mystery into something familiar, something woven into their daily experience. The galaxy was too vast to measure, too bright to ignore, so it became a mirror. Whatever mattered most to a culture found its reflection in that band of light. And yet, despite the differences, certain themes recur again and again. Rivers appear in story after story, from the Silver River in China to the Mayu in the Andes. Pathways recur as well, from the spirit road of the Lakota to the road of migrating birds in Europe. Backbones, spines, trees, structures that connect and support also appear. It seems that when people tried to make sense of the Milky Way, they reached for metaphors of connection, of pathways, of structures that link worlds together. Perhaps this is natural. The galaxy itself is a connection of countless stars. To see it as a bridge, a river, a road, is to sense, even without science, that it binds the cosmos into a whole. It's easy today to dismiss myths as simply quaint or mistaken, but they carry truths of their own. They tell us how deeply the night sky mattered to people, how present it was in their lives. Imagine trying to live without electricity, without screens, without constant artificial light. Night would not be a minor inconvenience. It would be half of every day, a realm filled with stars. Of course people would weave them into meaning. Of course the Milky Way would become a central symbol. To ignore it would have been impossible. Even now, when many of us rarely see the Milky Way at all, the stories still resonate. They remind us of our ancestors' relationship with the sky. They remind us that the galaxy isn't only an object to measure, but a source of wonder, of culture, of continuity. When we ask today how big it is, how many light years across, how many stars it contains, we're doing something similar to what they did. We're trying to make sense of the overwhelming, to put the infinite into terms we can understand. Their terms were rivers and backbones. Ours are numbers and models. Both are ways of bringing the galaxy closer, of making it part of human thought. Think of the power of seeing the Milky Way every clear night. It was a clock, a calendar, a compass, a storybook, a spiritual road. It was everything at once. And for cultures separated by oceans and continents, it was the same sight, inspiring different but strangely connected interpretations. That shared gaze across time and geography is remarkable. People who never met, who never heard of each other, told different stories about the same band of light, yet they all recognized its centrality. The Milky Way was always more than just stars, it was meaning. And that meaning continues. Astronomers today still speak of galactic rivers of stars, of pathways of gas and dust, of structures that bind galaxies into clusters. The metaphors of rivers and roads, born in myth, echo even in modern science. Perhaps that is inevitable. The galaxy resists easy description. Whether in ancient myths or modern equations, we reach for language that connects it to what we know. And in doing so, we keep alive a tradition that stretches back to the very first humans who looked up and wondered. For most of human history, the stars were points of light, and the Milky Way was a glowing path, explained with story and imagination. Then something remarkable happened. Humans learned how to bend glass in just the right way so that distant objects appeared closer. At first, these devices were curiosities, made for looking at ships on the horizon or landscapes far away. But soon enough, someone thought to point one at the sky. That simple act changed not only our understanding of the Milky Way, but the entire way we saw the universe. The invention of the telescope in the early 17th century marks one of the most important shifts in astronomy. Before it, observers had only their eyes. With it, the heavens suddenly expanded. Stars that had seemed few became countless. Planets that had looked like bright points revealed surfaces, moons, and features never suspected. The moon turned from a smooth, perfect disk into a rugged world of craters and mountains. Jupiter, once just a bright wandering star, became a miniature solar system with its own orbiting moons. And the Milky Way, that faint mist across the night sky, dissolved into uncountable stars when viewed through a telescope. Galileo Galilei is perhaps the most famous name tied to this revolution. In 1609, he built his own telescopes based on designs that had recently emerged in the Netherlands. They were crude by modern standards, with lenses that distorted and magnifications that seem small to us now. But compared to the naked eye, they were a revelation. Galileo pointed his telescope at the moon, at Jupiter, at Venus, and finally at the Milky Way. What he saw there must have been overwhelming. He described the band of light as a congeries of innumerable stars, far more than anyone had suspected. What had seemed like a cloudy streak was in fact an ocean of suns. This moment cannot be overstated. For millennia, people thought of the Milky Way as a singular thing, a mist, a cloud, a path. Galileo revealed it as a population. It wasn't one object, it was many. Not dozens, not hundreds, but thousands upon thousands, stars too faint to be seen individually by eye. That realization opened the door to an entirely new way of thinking about the cosmos. If the Milky Way was made of countless stars, then how big must it be? How many stars might be hidden beyond the reach of his telescope? And what exactly was our place among them? Other astronomers quickly followed. Johannes Kepler, already famous for his laws of planetary motion, took an interest in the telescope and used it to refine his ideas about celestial mechanics. Though Kepler didn't observe the Milky Way as extensively as Galileo, he recognized that telescopes had transformed the possible. Suddenly, the old models of a finite crystal sphere universe seemed small. The sky was no longer a dome but an expanse. Across Europe, telescopes spread rapidly. Wealthy patrons funded larger instruments. Scientists competed to see more, to record more. With every improvement, the Milky Way revealed new layers of complexity. Fainter stars, clusters, and eventually the dark lanes of interstellar dust became visible. What had once been an unbroken glow was shown to be structured, varied, dynamic. Still, the telescope didn't provide immediate clarity. In fact, it made the universe more confusing at first. If the Milky Way was filled with stars, how far away were they? Were they all part of one system, or did the galaxy extend indefinitely? And what were the faint nebulae, cloudy patches scattered across the sky? Some seemed part of the Milky Way, but others didn't. Were they nearby clouds of gas, or distant star systems of their own? The telescope showed more, but it didn't explain more. It forced astronomers to ask new questions, to confront mysteries they hadn't even known existed. For the everyday person of the 17th century, the telescope must have been a marvel. Imagine being invited to look through one for the first time. You lean over, squint into the eyepiece, and suddenly the moon is no longer a flat disk, but a world with mountains and valleys. Or you see Jupiter, a tiny dot transformed into a planet with 4 bright companions circling it night after night. The experience would have been breathtaking, even disorienting. To look at the Milky Way and see it break apart into individual stars must have felt like watching fog dissolve into a crowd of people. Something vague and distant became vivid and populated. The implications extended beyond science. The telescope challenged established ideas about the heavens. If the moon had craters, then it wasn't a perfect divine sphere. If Jupiter had moons, then not everything revolved around the Earth. And if the Milky Way contained countless stars, then perhaps the universe was far larger than anyone had imagined. These discoveries stirred controversy, admiration, and sometimes fear. They shifted humanity's self-image. No longer were we at the unmoving centre of a small, neat cosmos. We were part of something much grander, less tidy, and far harder to grasp. Over the following centuries, telescopes grew larger and more powerful. By the 18th century, astronomers like William Herschel were using giant reflecting telescopes to probe the depths of the Milky Way. Herschel and his sister Caroline spent years methodically counting stars in different directions of the sky. Their work produced one of the first rough maps of the galaxy. Herschel proposed that the Milky Way was a flattened system of stars, shaped something like a disk, with the Sun located near the centre. He was partly wrong. We now know the Sun is offset from the galactic centre, but his efforts marked one of the first attempts to use telescopes not just to observe, but to measure and model the structure of our galaxy. Think about the patience involved in such work. Night after night, Herschel and Caroline would record the number of stars visible through their telescope in a particular patch of sky. They did this thousands of times, building up a picture of density and distribution. It was tedious, meticulous, and incredibly ambitious. Their results were imperfect, but they showed that the Milky Way was not uniform. It had shape, structure, concentration. It was not just a random scattering of stars, but something organised. In addition to mapping stars, telescopes revealed new mysteries. The faint nebulae seen in the sky became a subject of intense debate. Some, when viewed with higher magnification, resolved into clusters of stars clearly part of the Milky Way. Others remained cloudy even under the best instruments. What were they? Gas clouds? Distant star systems? The telescope had opened the question, but the answer would not come until much later, when astronomers realised that many of these nebulae were in fact other galaxies far beyond our own. The expansion of telescopic astronomy also changed the way people thought about their place in the cosmos culturally. Artists, writers, and philosophers absorbed the new vision of a universe filled with stars. The Milky Way became not just a symbol of myth, but a symbol of infinity, of possibility. The Romantic poets of the 19th century wrote of it as a sea of suns, a metaphor for the boundlessness of imagination and human spirit. Science and culture fed each other, as the telescope inspired new ways of thinking about existence. Meanwhile, technical improvements kept pushing the frontier. Reflecting telescopes, which used mirrors instead of lenses, allowed for much larger instruments. Photography entered the scene in the 19th century, letting astronomers record what they saw and compare it over time. Long exposures revealed even more stars than the eye could detect through the telescope. Suddenly, the Milky Way appeared richer, denser, more crowded than anyone had guessed. The sheer number of stars became undeniable. Counting them was no longer even a consideration. The question shifted from how many to how are they arranged? How do they move? What holds them together? By the late 19th and early 20th centuries, telescopes had become so advanced that they could begin to measure stellar distances, motions, and properties. This was the beginning of astrophysics, where the telescope was not just a magnifier, but a tool for analysis. Spectroscopy, the study of starlight spread into its component colours, revealed the chemical makeup of stars. It showed that they were made of the same elements as the Sun, and therefore that the Milky Way was not composed of alien lights, but of suns like ours, scattered across immense distances. Looking back, the early age of telescopes was both exhilarating and humbling. Exhilarating because it multiplied the universe before human eyes. Humbling because each discovery seemed to reveal new layers of complexity. The Milky Way was not a single band of light, but billions of stars. Those stars were not identical, but varied in brightness, colour, and size. The galaxy was not random, but structured, and beyond it, perhaps, lay even more galaxies. Every answer produced more questions. It's worth pausing to think about how telescopes themselves were perceived in their time. They were not ordinary tools, they were almost magical. They allowed humans to see things no one had ever seen before, to bring the unreachable within reach. For a farmer or a sailor, looking through a telescope must have felt like stepping into another world. For a scientist, it was a gateway to discoveries that rewrote entire systems of thought. And for humanity as a whole, it was a shift in perspective as profound as any in history. Even today, when telescopes have grown into massive observatories and orbiting spacecraft, that sense of wonder persists. When the Hubble Space Telescope first turned its gaze on the Milky Way, it captured images filled with countless stars and nebulae, each one a reminder of Galileo's first realization. The glow of the Milky Way is still a congeries of innumerable stars, just as he said. But now we can see them in colours and detail he could never have imagined. And so, when we think about how telescopes changed everything, we are not only talking about a scientific revolution, we're talking about a change in consciousness. Before telescopes, the Milky Way was a story, a myth, a mystery. With telescopes, it became a system, a structure, a problem to study. But it never lost its beauty. If anything, it became more beautiful, because now we know that each faint glimmer is a world of its own, each star potentially with planets, each patch of light a reminder of scale. The telescope did not strip away the magic, it deepened it. And as telescopes improved, the next steps became possible, measuring the galaxy's shape, estimating its size, and understanding the motion of stars within it. Those efforts would carry astronomy into new eras, and the Milky Way, once a mythic river of light, would become a galactic system measured in light years. By the time telescopes had revealed the Milky Way as a dense field of stars, a new and unsettling question appeared. If the Milky Way was not a cloud, not a trail of mist, but a vast collection of suns, then what exactly was it? Was it the entire universe, or just a part of something larger? And more importantly, where did we fit into it? It's easy today to open a book or a website and see diagrams showing the Milky Way as a spiral galaxy, with the sun marked as a small dot about halfway from the centre to the edge. But that clear picture is very recent in the grand scale of human history. For centuries, astronomers had no certainty about whether we were inside the Milky Way, outside of it, or whether the Milky Way itself was the whole of creation. The discovery that we are not just looking at the Milky Way but living within it took generations of careful thought and sometimes bitter debate. When William Herschel mapped stars in the late 18th century, his work suggested that the Milky Way was a flattened system shaped like a disk. By counting stars in different directions, he thought he could infer the boundaries of the system. His conclusion was that we lived near the centre of this flattened disk. It was a bold attempt, and in some ways a breakthrough, but it was incomplete. Herschel didn't know about interstellar dust, which blocked light and made distant stars invisible. His map looked neat, but it was distorted by that unseen veil. Still, Herschel's idea that the Milky Way was a system of stars and that the sun was part of it was revolutionary. It was one of the first clear statements that we're not outside looking at the galaxy as an object, but inside it, surrounded on all sides by stars. To imagine what this realization feels like, think of standing in a dense forest. At first, you might think you're at the edge, looking into a wall of trees. But then you realize you're not at the edge at all. You're inside the forest, trees stretching in every direction. That's what the Milky Way is. Not a wall of stars at the horizon, but an ocean of stars in which we are immersed. Through the 19th century, this concept became more widely accepted. The Milky Way wasn't a backdrop or a distant band. It was the structure that contained us. The sun was one star among countless others, circling within a vast star system. But how vast and what shape it truly had were still open questions. Part of the difficulty was perspective. Imagine again being inside a forest and trying to sketch its shape. From your position on the ground, you see trees stretching in every direction. You can't climb high enough to see the outline of the entire forest. You can only guess based on density, spacing, and shadows. That was the astronomers' challenge. We couldn't step outside the Milky Way to photograph it. We had to infer its structure from the inside by counting stars, measuring light, and watching motions. At the same time, the question of whether the Milky Way was the whole universe, or just part of it, lingered. Those mysterious nebulae seen through telescopes were a major part of the puzzle. Some astronomers believed they were gas clouds within the Milky Way. Others suspected they might be island universes, entire galaxies beyond our own. This debate simmered for decades, because telescopes could not yet resolve the question. The Milky Way was clearly vast, but was it the entirety of the cosmos, or just one system among many? The turning point came in the early 20th century. Astronomers like Harlow Shapley began using new techniques to measure distances. Shapley studied globular clusters, dense groups of old stars found around the Milky Way. By estimating their distances, he discovered that they formed a roughly spherical distribution centred far from the Sun. This meant that the Milky Way was much larger than previously thought, and crucially, that the Sun was not at its centre. Instead, we were located far out toward the edge, tens of thousands of light years away from the middle. This was a humbling discovery. For centuries, humans had imagined themselves at the centre of the universe. Even Herschel's model had placed the Sun near the centre of the Milky Way. Shapley's work showed otherwise. We were off to the side, in a quiet suburb of the galaxy. The Milky Way was vast, perhaps 100,000 light-years across, and we were not privileged at its heart, but drifting far away from it. The psychological impact was profound. First, Copernicus had removed Earth from the centre of the solar system. Now Shapley removed the Sun from the centre of the galaxy. Once again, humanity had to adjust to a smaller, less central role in the cosmic story. At the same time, the realization that we lived inside the Milky Way clarified many mysteries. The band of light across the sky was no longer just a curiosity. It was the dense disk of stars seen edge on from within. When we look toward the galactic centre in the constellation Sagittarius, we see the thickest concentration, crowded with stars and clouds of gas and dust. When we look perpendicular to the disk, the Milky Way appears thinner. This perspective explains the uneven glow and the patterns of dark rifts within it. We are seeing our galaxy from the inside, our vision shaped by dust and distance. The next great leap came in the 1920s, when Edwin Hubble used the Mount Wilson Observatory's giant telescope to settle the debate about other galaxies. By studying the Andromeda Nebula, he proved it was not a cloud within the Milky Way, but a separate galaxy, millions of light-years away. The Milky Way was vast, yes, but it was not the entire universe. It was just one galaxy among many. This revelation built on Shapley's discovery. Not only were we not at the centre of the Milky Way, but the Milky Way itself was not at the centre of the universe. It was one among billions. But even with that broader context, the fact remained. We live inside the Milky Way. Every star you see at night, except for a handful of nearby galaxies visible as faint smudges, is part of this single system. The constellations, the familiar patterns of Orion, the Big Dipper, Scorpius, they're all part of the Milky Way. Our sun, our planets, our history, every human who ever lived, all of it has taken place inside this one galaxy. When you think about that, it changes the way you see the night sky. You're not looking at decorations pinned to a dome. You're looking along the inside of a structure that wraps around you. The stars are not flat on a surface. They're spread out in depth, scattered across thousands of light years, arranged in arms and clusters. The Milky Way is not a picture on the sky. It is a three-dimensional home, and we are living inside its walls. This perspective also helps explain why counting stars by eye was always futile. When you look at the Milky Way, you're not just seeing stars nearby. You're seeing through layers upon layers, some close, some unimaginably far away. They overlap, blend, and crowd together, making it impossible to distinguish them individually. That's why the galaxy looked like a mist for so long. The telescope pulled it apart, but even then the sheer number of stars defied complete counting. Living inside the Milky Way also means that we are moving with it. Our sun is not fixed in place. It orbits the galactic centre at an incredible speed, nearly 828,000 kilometres per hour. Yet even at that speed, it takes about 225 million years to complete a single orbit. That means that since the Sun formed 4.6 billion years ago, it has circled the galaxy only about 20 times. Every creature that has ever lived on Earth, from the earliest microbes to us, has done so while riding along inside this slow orbit. We are passengers on a journey so vast that no human lifetime can sense its progress. Understanding that we live inside the Milky Way changes the way we think about home. Home is not just Earth. It is not even just the solar system. It is the galaxy itself, the great spiral of stars and dust and dark matter that surrounds us. It's not a backdrop, it's a structure, and we are embedded in it. The ancients looked up and told stories about the Milky Way as a road, a river, a backbone. In their way, they were right. It is all of those things, but on a scale they could never have imagined. And so, little by little, through glass lenses, careful counting and patient measurements, we came to realise that we're not looking at the Milky Way from afar. We are inside it, wrapped in its arms, moving with it through the universe. It is not only our view of the night sky, it is our address in the cosmos, and that realisation set the stage for the next questions. What is its shape? How do its arms curve? And how do we map a galaxy we cannot step outside to see? Once it was clear that we live inside the Milky Way, a new puzzle emerged. If we are part of this immense system, then what does it actually look like? From Earth, the galaxy presents itself as a glowing band, thicker in some places, thinner in others, with dark patches breaking up the light. That view tells us we're inside something flat and extended, but it doesn't reveal the full shape. The problem is perspective. We cannot step outside the Milky Way to take a photograph of it from above. We have to build the picture indirectly, through measurements, patterns, and comparison. The earliest attempts to imagine the Milky Way's form were based on counting stars. William Herschel's careful surveys in the late 18th century suggested a flattened distribution, like a disk. By looking in different directions and tallying how many stars appeared, he noticed that some regions were dense and others sparse. From this, he sketched the galaxy as a wide lens-shaped system, thicker in the middle and thinner at the edges. His diagram was primitive by modern standards, but it was one of the first efforts to reduce the Milky Way to a recognisable shape. To Herschel, it looked like a flat disk of stars with the sun somewhere near the middle. Later, astronomers realised that Herschel's map had blind spots. Dust clouds running through the galaxy blocked light, hiding distant stars. What looked like an edge might simply have been the limit of visibility. Still, the idea of a disk was correct. Stars were not arranged in a sphere around us, nor scattered evenly in all directions. They were flattened, arranged in a vast rotating system. By the 19th century, telescopes had become powerful enough to show that other spiral-shaped nebulae existed. Some astronomers wondered whether the Milky Way might be a spiral too, but the question was unsettled because it was still unclear what those nebulae were. Were they nearby clouds of gas? Or were they galaxies of their own? Without clarity, the idea of a spiral Milky Way remained speculation. It wasn't until the 20th century that firm evidence emerged. Astronomers began measuring the positions and motions of stars, trying to trace larger structures. They noticed that many stars seemed to cluster along curved paths. The development of radio astronomy after World War II was particularly important. By tuning into the radio waves emitted by hydrogen gas, astronomers could see through the dust that blocked visible light. Suddenly, the Milky Way's hidden structure came into view. What they found was astonishing. The Milky Way is not just a disk. It is a spiral galaxy, with long arms curving outward from a central bulge. These arms are where gas, dust and young stars gather, forming glowing regions of starbirth. Our own Sun is not in the bulge, nor in the very outer rim, but partway out, sitting in a minor arm known as the Orion Arm, tucked between two of the larger spirals. The galaxy has 4 major arms: the Perseus Arm, the Scutum Centaurus Arm, the Norma Arm, and the Sagittarius Arm, along with several smaller ones. From within, we see them as patches of dense stars and nebulae. From outside, they would appear as graceful swirls. Mapping these arms has been a slow, painstaking process. Astronomers use parallax, measuring tiny shifts in a star's position as Earth orbits the Sun, to calculate distances. They use variable stars like Cepheids, whose brightness cycles reveal their distance. They use radio emissions from hydrogen and molecular gas to trace structures invisible to the eye. Each method contributes a piece to the puzzle. Piece by piece, a picture emerges of a galaxy about 100,000 light-years across, with a bulging centre, a thin disk of stars and gas, and faint spiral arms extending outward. The bulge itself hides secrets. At its core lies Sagittarius A, a supermassive black hole weighing millions of times the mass of the Sun. We can't see it directly, but we can measure the orbits of stars whipping around it at incredible speeds, proving its presence. Surrounding this heart is a dense region of older stars, packed so tightly that they blur together even in powerful telescopes. Beyond the disk, a halo of stars and globular clusters extends outward. These clusters are among the oldest objects in the galaxy, containing stars that formed billions of years ago. They orbit in spherical patterns surrounding the disk like bees around a hive. Beyond them lies an even more mysterious halo of dark matter, unseen but detectable through its gravitational pull. This invisible mass outweighs the stars and gas, shaping the galaxy's overall form. The discovery of spiral arms was more than a matter of mapping. It was a revelation of process. Spirals are not static structures, but patterns of density, like traffic jams that persist even as individual cars move through them. Stars form in the dense regions, live their lives and drift onward, while the spiral pattern remains. This means the Milky Way is not just a shape frozen in time. It is a living, dynamic system, constantly changing, yet maintaining an overall form. For a person lying under the night sky, the spiral structure is invisible. You see a bright band, thicker near Sagittarius, thinner near Orion, and perhaps, if you're lucky, patches of nebulae glowing faintly. You can't see the swirl because you're inside it. But with instruments, with decades of patient measurements, astronomers have revealed that our galaxy is one of those elegant spirals so often captured in images of the universe. The difference is that this one is ours, and we are looking out from its middle. When you think about this, it's remarkable how far we've come. From Aristotle believing the Milky Way was a kind of atmospheric fire, to Herschel sketching a disk of stars, to modern radio telescopes tracing spiral arms through invisible hydrogen, the progression shows the power of curiosity and persistence. Each generation of observers built on the last, correcting mistakes, refining maps, expanding the picture. Today we can generate computer models of the Milky Way, simulating billions of stars in motion, showing the galaxy from every angle. Even though no one has ever seen it from outside. And yet, despite all these advances, mysteries remain. How many arms does the Milky Way truly have? Some studies suggest 2 main arms, others 4. The Orion Arm, where we live, is sometimes described as a spur, sometimes as a branch. Even with all our tools, the galaxy's full structure is still being uncovered. Like explorers mapping a continent from within its forests, we're still tracing the rivers and mountains, still filling in the blank spaces on the map. Understanding the shape also connects us to other galaxies. When we look at the Andromeda Galaxy, or the Whirlpool Galaxy, or countless spirals captured by Hubble, we are seeing analogues of our own home. Their arms, bulges, halos, all mirror what we believe exist in the Milky Way. By studying them, we refine our understanding of ourselves. By studying ourselves, we interpret them. The exchange is constant. For everyday life, the shape of the Milky Way may seem abstract, but it carries a quiet resonance. To know that we live in a spiral galaxy, that we are riding one of its arms, is to place ourselves within a grand design. The spiral is one of nature's recurring patterns found in shells, hurricanes, and galaxies alike. To discover that our home shares this form is to feel connected to something universal. So when we ask whether the Milky Way is a disk, a spiral, or something else, the answer is layered. It is a disk, flattened and rotating. It is a spiral with arms of stars and gas curving outward. It is also something else, a system wrapped in dark matter, with a bulging heart, a surrounding halo, and constant motion. No single word captures it fully, but together these images bring us closer to understanding. And as the picture sharpens, the next questions arise. What are these spiral arms like up close? How do stars cluster along them? What is it like to live in one arm of a galaxy while seeing others only faintly across the dark? When astronomers first realized that the Milky Way is a spiral galaxy, it was like learning that your home is not just a building but part of a whole city with districts and neighborhoods. Suddenly, the band of light overhead wasn't just a uniform glow. It had structure, arms that wrapped around the galactic center filled with stars, gas, dust, and movement. These spiral arms became one of the most important discoveries in understanding the galaxy, because they reveal not only how it looks but how it works. The Milky Way's arms are not solid objects, nor are they permanent lines. They are more like patterns of density, regions where stars and gas are more concentrated, where new stars are born, and where the galaxy's spiral form becomes visible. Imagine driving in heavy traffic. The cars move, but the traffic jam itself seems to hold its shape as vehicles enter and leave it. The spiral arms are like those traffic jams, waves of density in which stars and gas crowd together for a time before drifting on. This idea, known as the density wave theory, explains how the arms persist even though stars are constantly moving. The Milky Way has 4 main arms, each sweeping outward from the central region. They are named after constellations in the directions they point: the Perseus arm, the Scutum Centaurus arm, the Norma arm, and the Sagittarius arm. Between them are smaller arms and spurs, including the one we live in, the Orion arm. Our solar system orbits the galaxy about halfway between the centre and the edge, and we find ourselves not in one of the giant arms but in a smaller branch. It is like living in a quiet side street rather than on a busy downtown boulevard. Each arm is a bustling neighbourhood on a galactic scale. They are sites of intense star formation. Clouds of hydrogen gas, stretching across hundreds of light years, collapse under their own gravity, igniting new stars that shine hot and bright. These young stars, often grouped in clusters, light up the arms, giving them their luminous appearance. Nebulae, glowing with ionized gas, add colour and complexity. The famous Orion Nebula, visible even to the naked eye as a faint smudge in Orion's sword, is one such star-forming region, part of the Orion Arm. To picture what an arm is like, imagine drifting through space in a ship that could travel light years in comfort. You would pass through great clouds of gas and dust, sometimes dense and opaque, sometimes thin and faint. In these clouds, new stars would be forming, their light carving cavities in the gas. You'd see clusters of young blue stars, brilliant but short-lived, burning their fuel rapidly. You'd see older, redder stars scattered more sparsely, survivors of earlier generations. The arms are places of constant renewal, where the galaxy's cycle of birth and death plays out most vividly. Astronomers trace the arms using several methods. Bright young stars and star clusters act as markers, since they are born in the arms and don't live long enough to drift far away. Giant clouds of molecular hydrogen also serve as signposts, mapped through radio waves. Even masers, natural cosmic lasers of microwave radiation from molecules, help pinpoint distances and locations within the arms. By combining these techniques, astronomers have gradually built a map of the Milky Way's spiral structure, though it remains incomplete. The arms are vast, and our view from within makes the mapping slow and challenging. Our position in the Orion arm has both advantages and drawbacks. On the one hand, it means we are in a relatively quiet region, not too crowded with massive stars or destructive events. On the other hand, it means we cannot see the galaxy's spiral structure directly. We see only cross-sections, bands of stars that hint at curves beyond our sight. To glimpse the full grandeur of spiral arms, we must look at other galaxies, like the Andromeda Galaxy or the Whirlpool Galaxy, which show the sweeping patterns we can only infer for our own. Still, even from our vantage point, the spiral arms affect us. The Sun orbits the galactic centre every 225 million years, and in that time it passes in and out of different arms. This means that the environment around the solar system changes over cosmic timescales. Sometimes we drift through quieter inter-arm regions with fewer nearby stars. Sometimes we plunge into denser arms, where star formation is active and cosmic radiation is higher. Some scientists have even speculated that these passages may influence conditions on Earth, perhaps affecting climate or even mass extinctions, though such connections remain debated. What's certain is that the spiral arms are not just pretty structures, they're engines of galactic evolution. Without them, stars would still form, but the arms organise and concentrate the process. They act as nurseries, gathering gas and dust into dense regions where gravity can work its magic. The arms also serve as highways of sorts, channels along which stars and gas move, shaping the galaxy's long-term dynamics. To think about the scale of an arm, consider this. The Orion arm, our home region, is thousands of light-years wide and tens of thousands of light-years long. That's just a minor arm. The major ones stretch far larger, each containing millions of stars and countless solar systems. If you tried to cross one at the speed of light, it would take tens of thousands of years. These are not features you can traverse in any human sense. They are landscapes on a cosmic scale, slow-moving but immense. The beauty of spiral arms also lies in their variety. No two are alike. Some are broad and bright, crowded with stars. Others are thin and faint, barely outlined against the galactic disk. Some branch, split or twist. The arms are not rigid. They are fluid, shaped by gravity, rotation, and the distribution of matter. Over millions of years they shift, grow and fade, though the overall spiral pattern endures. And within those arms, life unfolds. Planets form around newborn stars. Some of those planets may develop conditions for life, others may remain barren. From our perspective, the spiral arms are remote structures, but for beings who might live on distant worlds, they are home. Somewhere in the Perseus arm, perhaps, civilizations may be looking out at their night skies, seeing their own view of the Milky Way, wondering what lies beyond. In that sense, the spiral arms are not just neighbourhoods of stars, but potentially neighbourhoods of life. When you lie under the night sky and see the Milky Way stretching above, you're glimpsing these arms in cross-section. The dense band through Sagittarius is the direction of the galactic centre, where multiple arms converge. The patches of bright nebulae in Cygnus and Orion are part of our own local arm. The glow is not uniform because the arms are not uniform. Some regions shine with new stars, others are dimmed by dust. Together they form the great swirl that defines our galaxy. Understanding the spiral arms also helps us place the Milky Way in context. Not all galaxies are spirals. Some are elliptical, smooth and featureless, with little gas and no new star formation. Others are irregular, chaotic, lacking symmetry. Spirals with their graceful arms are among the most beautiful, and we are fortunate to live in one. The arms give structure to our sky, even if we can't see the full pattern directly. They give us the Orion Nebula, the Eagle Nebula, the Lagoon Nebula. windows into the galaxy's creative processes. For astronomers, the arms remain a subject of ongoing research. How exactly do they form? Are they driven by density waves, by interactions with companion galaxies, or by internal processes of star formation? How stable are they over billions of years? These are questions still being studied, used in simulations, observations, and comparisons with other galaxies. The answers are complex, but the pursuit itself reflects our drive to understand the structure we call home. And for those of us simply gazing upward, the spiral arms remind us of scale and belonging. We are not isolated. We are part of a neighbourhood, a cluster of stars travelling together in the great swirl of the Milky Way. Our sun is one of countless others, shining quietly alongside them, sharing the same galactic journey. The arms may be vast, but they include us. When you look toward the constellation Sagittarius on a clear summer night, you're looking in the direction of the Milky Way's heart. It's the thickest, brightest region of the galaxy as seen from Earth, a crowded portion of the band where stars and clouds of dust gather in dazzling density. And yet, strangely, even though this is the centre of our galaxy, we cannot actually see it directly. The reason is simple, but frustrating. Dust. The Milky Way is full of dark, obscuring clouds of interstellar material, and the line of sight toward the galactic centre passes through thousands of light-years of them. Visible light from the core is absorbed and scattered, leaving us blind to what lies at the heart of our own galaxy. To the naked eye, the region looks like a busy patch of stars, bright but not extraordinary. But behind that veil, hidden from ordinary vision, lies one of the most important and dramatic regions in the cosmos. The galactic centre is about 26,000 light-years away from Earth. It contains a dense bulge of stars, a crowded sphere where millions of suns are packed into a relatively small volume of space. Stars there are much closer together than in our local neighbourhood. If you live near the centre, your night sky would blaze with hundreds of bright stars visible at once, far more than we ever see here. It would be a sky alive with light, every patch filled with neighbours. The contrast to our quiet outskirts would be stunning. At the very core, though, something strange awaits. We now know that a supermassive black hole resides there, a gravitational monster millions of times heavier than our Sun. This black hole, called Sagittarius A, is invisible directly, but we infer its presence from the way stars orbit around it. Some of these stars move at incredible speeds, whipping around in tight paths that only such a massive, compact object could cause. By tracking their orbits over decades, astronomers have been able to calculate the black hole's mass with precision. It is about 4 million times the mass of the Sun, contained in a space smaller than our solar system. But before this picture became clear, the galactic centre was a mystery for centuries. Early astronomers knew it was a dense region, but they couldn't see through the dust. Only when technology expanded into other wavelengths of light did the heart begin to reveal itself. Infrared astronomy, which can penetrate dust, showed stars hidden from view. Radio astronomy revealed emissions from gas swirling around the core. X-ray telescopes detected bursts of high-energy radiation from matter being consumed by the black hole. Piece by piece, an invisible centre became visible, not to our eyes, but to our instruments. The discovery of Sagittarius A in the 1970s was a turning point. Using radio telescopes, astronomers identified a compact, bright source of emission right at the galactic centre. It wasn't a star, it wasn't a nebula. It was something much stranger. Over time, careful measurements of nearby stars confirmed the presence of a supermassive black hole. In 2020, the Nobel Prize in Physics was awarded to researchers who had tracked these stars, proving the black hole's existence beyond doubt. It was one of the strongest confirmations of general relativity and a milestone in our understanding of galaxies. Imagine what it means. At the heart of our home galaxy lies a black hole, an object so dense that not even light can escape. Everything in the Milky Way, the stars, the gas, the spiral arms, even us, moves under the influence of its gravity. We orbit the galactic centre because of it. Without that mass anchoring the galaxy, the stars would drift apart. The black hole is not a threat to us, since we are far away on the galactic outskirts, but it is central to the structure and dynamics of the Milky Way. It is, in a way, the galaxy's anchor. But the galactic centre is not defined only by the black hole. It is a dynamic environment of extraordinary complexity. Dense star clusters crowd the region, including some of the most massive known in the galaxy. Gas clouds swirl and collide, feeding bursts of star formation. High-energy phenomena, supernovae, flares, radiation, fill the area with activity. To live near the galactic centre would be to live in a cosmic metropolis, noisy and crowded, in stark contrast to our quiet neighbourhood in the Orion Arm. And yet, from Earth, all of this remains hidden behind dust. The irony is striking. We can see galaxies millions of light years away in great detail, yet the centre of our own galaxy is veiled. To study it, we rely on telescopes that observe in infrared, radio and X-rays, looking past the dust to glimpse the drama inside. The Event Horizon Telescope, a worldwide network of radio dishes, even managed to capture an image of Sagittarius A in 2022, showing the shadow of the black hole's event horizon for the first time. It was a triumph of global collaboration, a reminder that even the hidden heart of our galaxy can be revealed with persistence. The hidden nature of the galactic centre has also fueled imagination. For centuries, when people saw the thick glow in Sagittarius, they could only wonder, was it the seat of the gods? A portal to another realm? A furnace where stars were forged? Even now, knowing it contains a black hole doesn't make it less mysterious. If anything, it makes it more so. Black holes are objects that stretch our understanding of physics. At their cores, our current theories break down. To say that one lies at the heart of the Milky Way is to say that our galaxy itself is centred on a paradox. Consider what it means to live in such a galaxy. Every orbit of the sun, every spiral of the arms, every motion of stars is tied to the gravity of the hidden heart. We are, all of us, moving in response to something we cannot see directly. It is a reminder that the universe holds depths far beyond what meets the eye. The familiar night sky is only the surface. Beneath it lie structures and forces invisible but real, shaping everything we know. The galactic centre also raises questions about the life of galaxies. How do supermassive black holes form? Do they grow by swallowing stars and gas, or by merging with other black holes? What role do they play in galaxy formation? We know that nearly every large galaxy hosts one, suggesting a deep connection between galaxies and their central black holes. To understand one is to understand the other. Our own galactic centre is a laboratory for these questions, close enough to study in detail, even if hidden from our eyes. From a human perspective, the idea that we orbit an invisible black hole may sound unsettling, but in practice, it's no more threatening than orbiting the sun. Gravity binds us in stable motion, and at our distance the black hole's influence is felt as a steady pull, not a danger. If anything, it is reassuring. The galaxy holds together because of it. It gives the Milky Way its coherence, its structure, its rhythm. Without it, the spiral arms would not endure, the disk would not remain bound, and yet the centre is not static. Over millions of years, gas falls toward the black hole, sometimes flaring as it is consumed. Stars drift closer, some torn apart, their debris swallowed. At times, the black hole may have been more active, blasting jets of energy into the galaxy. Today it is relatively quiet, but evidence suggests that in the past it may have lit up as a quasar, outshining the rest of the galaxy. What we see now may just be a calm phase in a long cycle of activity. The hidden heart of the Milky Way is both an anchor and a mystery, both stable and dynamic. It is the core of our home, yet invisible to us without technology. To think about it is to confront the limits of perception, the gap between what we see and what is. The ancients looked at Sagittarius and saw stories. We look with telescopes and see stars, clusters, and a black hole. Both views remind us that the centre is not ordinary. It is extraordinary, the beating heart of the galaxy, shaping everything around it. And as we linger on this thought, the natural question follows. What exactly is this black hole? Sagittarius A. How does it work, and what does it mean for the galaxy that such a monster sits at its core? At the heart of the Milky Way, behind layers of dust and crowded fields of stars, lies one of the most fascinating objects in the cosmos, Sagittarius A. The name comes from the constellation Sagittarius, the direction in which the galactic centre lies, and the symbol indicates a radio source. To most people it might sound like a piece of technical shorthand, but in reality it refers to a supermassive black hole, a gravitational giant millions of times the mass of the Sun. This object is the anchor of our galaxy, and even though it is invisible to our eyes, its presence is felt everywhere. When astronomers first discovered Sagittarius A in the 1970s, they didn't know immediately what it was. Using radio telescopes, they noticed a compact, unusually bright source of emission at the centre of the galaxy. It was too small to be a star cluster, too energetic to be an ordinary star. Over time, observations revealed that stars very close to the centre were moving in tight, rapid orbits. These stars, known as the S-stars, provided a natural experiment. By tracking their motions carefully, astronomers could measure the invisible mass pulling on them. What they found was staggering. The orbits pointed to an object about 4 million times the mass of the Sun, confined within a region smaller than our solar system. No ordinary star, no cluster, no cloud could fit those numbers. The only explanation was a supermassive black hole. This was not just theory. It was direct evidence. Decades of measurements, carried out with incredible precision, showed stars whipping around the unseen centre at speeds of thousands of kilometres per second, tracing paths predicted by Einstein's general relativity. Sagittarius A is not alone in the universe. We now know that nearly every large galaxy has a supermassive black hole at its core. Some are much larger, billions of solar masses, powering quasars so bright they outshine their entire galaxies. Our black hole is relatively modest by those standards, but its closeness makes it unique. It is the only supermassive black hole we can study in such detail, the only one where we can track individual stars orbiting in real time. For astrophysics, it is like having a laboratory for extreme gravity just 26,000 light-years away. The nature of a black hole is both simple and mind-bending. It is a region of space where gravity has become so intense that nothing, not even light, can escape. The boundary of this region is called the event horizon. Once something crosses it, it cannot return. At Sagittarius A, that horizon is about 25 million kilometres across, or about the size of Mercury's orbit around the Sun. For an object holding 4 million solar masses, that's surprisingly compact. All of that matter, all of that gravity, squeezed into a point where space and time themselves are warped. And yet, despite the drama of its nature, Sagittarius A is quiet by cosmic standards. It is not actively feeding on vast amounts of gas as some black holes do. It does consume matter occasionally, as gas clouds drift too close and fall inward, heating up and producing flares of X-rays and radio waves. But compared to the raging quasars seen in distant galaxies, Sagittarius A is subdued. It slumbers most of the time, glowing faintly in radio and infrared, erupting only occasionally with bursts of energy. The Event Horizon Telescope, a global network of radio observatories linked together, made history in 2022 by capturing the first image of Sagittarius A. It showed a ring of glowing material, light bent by gravity into a circle around a dark centre, the shadow of the black hole itself. This was not an artist's impression or a theoretical model. It was a photograph, built from data gathered across Earth, revealing the shape predicted by Einstein a century earlier. For many, it was a moment of awe. humanity had finally seen the outline of the monster at the centre of its own galaxy. To understand how profound this is, think about what it means to take a picture of something invisible. The black hole itself emits no light. What we see is the hot plasma swirling around it, accelerated to near-light speeds as it spirals inward. Light from this material is bent and distorted by the black hole's gravity, producing the ring shape. The darkness in the middle is the absence of returning light, the event horizon's shadow. This image confirmed not only the existence of Sagittarius A, but the reality of black holes as predicted by theory. Yet the story of Sagittarius A is not only about physics, it also shifts the way we think about home. At the core of our galaxy, the place around which all stars orbit, lies an object that is fundamentally unknowable. We can measure it, photograph it, even simulate it, but we cannot experience it directly. It represents a limit, a place where our understanding of nature breaks down. To live in a galaxy with such a heart is to live in a universe where mystery is not just distant but central. The stars around Sagittarius A tell their own story. Some of them swing in and out in tight elliptical orbits, completing a loop in just a few decades. Their paths curve dramatically as they approach the black hole, like comets around the sun but far more extreme. These stars are witnesses to the black hole's presence, their dance a silent testimony to the gravity at work. Watching them over time is like watching clock hands sweep around a dial, marking out the rhythm of a hidden force. Occasionally a star ventures too close. In those rare events, tidal forces from the black hole can tear the star apart, scattering its gas into space. Some of that material falls inward, lighting up briefly before vanishing. These events, known as tidal disruption events, have been seen in other galaxies. At our centre, they are rarer, but the possibility is always there. The black hole is patient, waiting silently, its appetite endless but unpredictable. The quiet nature of Sagittarius A. Today does not mean it has always been so. Evidence suggests that in the past, the black hole may have been much more active, blazing as a quasar that poured energy into the galaxy. Structures called the Fermi bubbles, giant lobes of gamma-ray emission extending above and below the Milky Way, may be relics of that time, scars left by past eruptions. If so, then our calm black hole once shone with a brilliance that would have made the galaxy glow. What we see now may be only a pause in a much longer cycle of activity. Living in the outskirts of the galaxy spares us from the extremes of the central environment. Near Sagittarius A, radiation levels are higher, star density is intense, and gravitational interactions are common. Planets in that region would experience skies far brighter than ours, filled with stars packed closely together. Whether such conditions would allow life to thrive is an open question. But for us, 26,000 light-years away, the black hole is distant enough to be only a curiosity, not a threat. We circle it once every 225 million years, pulled along with billions of other stars, passengers in a vast orbit. The existence of Sagittarius A also deepens our understanding of galaxies in general. Its presence confirms that supermassive black holes are not exotic exceptions, but essential components of galactic structure. They influence star formation, regulate the flow of gas, and shape the evolution of their host galaxies. By studying Sagittarius A, we learn not only about our own home, but about galaxies everywhere. It is both unique and universal, particular to us, but also a model for others. And for all its mystery, it is strangely comforting to know it is there. At the core of the Milky Way lies something enduring, stable on human timescales, anchoring the galaxy across billions of years. We live in its orbit, bound by its gravity, part of its system. It is not a monster lurking in the dark, but a natural consequence of gravity and time, a feature of the universe that we are fortunate enough to understand, at least in part. As you imagine the galactic centre and the black hole within it, you might picture it not as a void, but as a presence. Silent, invisible, yet profoundly real. It is the heart of the Milky Way, and everything you know, everything you are, circles it endlessly. And from here, the next question arises. If this is the anchor of the galaxy, then how vast is the space it governs? How far do its stars and arms extend? And what does that mean when we speak of the Milky Way's true size? When we talk about the Milky Way, words like large or vast quickly lose their usefulness. Our minds are trained to handle the scale of everyday life, the length of a room, the distance to work, the number of steps it takes to cross a street. Even when we stretch to think of continents, oceans, or the circumference of Earth, the numbers remain within a framework that feels relatable. But galaxies push far beyond that framework. The distances involved are so enormous that ordinary units like kilometres or miles collapse into nonsense. It's here that astronomy turns to a different tool, the light year. A light year is the distance light travels in a single year. To picture it, start small. Light moves at about 300,000 kilometres every second. In the blink of an eye, in less than a heartbeat, a beam of light could circle the Earth more than 7 times. Multiply that speed by 60 to cover a minute, then by 60 again for an hour, then by 24 for a day, then by 365 for a year. By the time you finish the calculation, you've reached nearly 10 trillion kilometres. That's 1 light year. Already the number is absurd. 10 trillion is a number too large to hold in your head. You can write it down, count the zeros, but it slips away as soon as you try to picture it. And yet, when astronomers measure the Milky Way, they talk not in kilometres, but in tens of thousands of light years. The galaxy is about 100,000 light years across. That means a beam of light, the fastest thing in the universe, would take 100,000 years to travel from one side to the other. Imagine shining a flashlight across the galaxy tonight and waiting for its beam to reach the other edge. By the time it got there, human civilization as we know it would be unimaginably transformed. Empires would have risen and fallen, languages would have shifted, continents would have changed. 100,000 years is longer than all of recorded human history, and light would still just be arriving. Even the smaller distances within the galaxy overwhelm us. The Sun's nearest neighbour, Proxima Centauri, is 4.2 light-years away. At first glance, that might not seem like much, just 4 years of travel at light speed. But think about what that means in practical terms. The fastest spacecraft humans have ever launched, like the Parker Solar Probe, travel at tens of kilometres per second. Even at that blistering pace, reaching Proxima Centauri would take tens of thousands of years. A journey to the next nearest star is, with today's technology, as unreachable as crossing the galaxy itself. This mismatch between human imagination and cosmic distance is why numbers start to feel silly. We can say 26,000 light-years when describing the distance to the galactic centre, but what does that really mean to someone walking through their day? 26,000 years ago, humans were making cave paintings and hunting with stone tools. If light had left the galactic centre then, it would only just now be reaching us. To say that we live 26,000 light-years from the centre is to say that we see it not as it is now, but as it was when humanity was still in its deep prehistory. Every direction we look in the galaxy, we're seeing the past, frozen in light that has taken tens of thousands of years to reach us. Astronomers sometimes use analogies to make these numbers more approachable, though the analogy often collapses under the weight of the scale. One common image is to shrink the Milky Way to the size of a dinner plate. On that plate, our solar system would be smaller than the tip of a pencil. The distance to the nearest star would be a microscopic dot just beside it. Suddenly the galaxy feels huge again, even though we shrank it. The problem isn't the metaphor, it's that the reality is too big to fit inside metaphors. Think about time as well as space. When we say 100,000 light-years, we're also talking about 100,000 years of history. Every beam of starlight that reaches your eyes carries with it an age. The stars you see tonight may no longer even exist. Some may have exploded as supernovae thousands of years ago, but their light is still travelling, still showing you the star as it was, not as it is. In that sense, looking at the Milky Way is like looking into a time machine. You are never seeing the present. You are seeing thousands, tens of thousands, even hundreds of thousands of years into the past, depending on where your gaze falls. This time-lagged view makes the galaxy even stranger to imagine. Suppose a civilization were watching us from the other side of the Milky Way. They would not see Earth as it is today. They would see it as it was 100,000 years ago, before agriculture, before writing, before cities, before almost everything we think of as civilization. If we looked at them, we would see their world in its own prehistory. The vast distances make communication impossible, not only in space but in time. A message sent across the galaxy at the speed of light would not arrive until long after the sender was gone. The Milky Way is not just wide, it is ancient in the way it communicates, with signals stretched across millennia. For astronomers, grappling with these scales requires discipline. To measure distances, they use tools like parallax, watching how nearby stars shift slightly against the background as Earth orbits the Sun. For farther stars, they use standard candles, stars whose brightness reveals their distance. For still greater spans, they turn to the patterns of hydrogen gas, or to variable stars like Cepheids. Each method extends the cosmic ruler farther, until the galaxy can be mapped in light years. But behind the technical detail lies the same challenge. The numbers defy intuition, and yet these numbers are not meaningless. They allow us to compare, to build a sense of proportion. If the Milky Way is 100,000 light-years wide and the Andromeda Galaxy is 220,000 light-years wide, we begin to understand their relative sizes. If the Sun is 26,000 light-years from the centre, we can place ourselves within the disk. If stars in the spiral arms are only a few thousand light-years away, we can map their positions. Light-years let us handle the incomprehensible, even if only symbolically. Still, it is worth remembering that for ancient people, none of this was necessary. They looked up and saw the Milky Way without numbers, without scales, and still found it meaningful. They didn't need to know it was 100,000 light-years across to know it was beautiful. They didn't need to calculate distances to feel awe. In some ways, our knowledge deepens the wonder, but it also reminds us of our limits. We can name the numbers, but we cannot hold them in our minds. That might be the most important lesson of light years. They remind us of our smallness. To us, a kilometre is large. To the galaxy, it is nothing. To us, a human lifetime feels long. To the galaxy, it is a blink. The Milky Way is not measured in steps, days, or years. It is measured in light years, spans so vast that even the fastest speed in the universe takes tens of thousands of years to cross them. To live inside such a system is to live inside immensity, whether we realise it or not. And as we try to grasp these scales, the next question naturally arises. Where then do the edges lie? If the Milky Way is 100,000 light-years across, what defines its boundary? How do astronomers know when they've reached the edge, and what lies beyond it? When we say the Milky Way is about 100,000 light-years across, it sounds like a neat and certain measurement, a single figure, a clear boundary, as if the galaxy were a well-marked circle on a map. But in truth, the edges of the Milky Way are far more difficult to define. A galaxy is not like a continent, where land ends and sea begins. It is more like a cloud, its density fading outward, its structures blending into the larger universe. Asking, how far does the Milky Way really go, is not just a question of size. It is a question of where we draw the line between what belongs to our galaxy and what does not. The visible disk, the part most of us picture, is the easiest to describe. That is the flat arrangement of stars and gas, organised into spiral arms, stretching about 100,000 light-years from side to side. This is what creates the bright band across the night sky, the part mapped by telescopes and filled with familiar nebulae and clusters. From Earth, we see this disk edge on, which is why it appears as a streak. But even this disk is not sharply bounded. Its edges are ragged, irregular, with stars thinning out gradually rather than stopping suddenly. Beyond the disk lies the halo, a vast spherical region filled with old stars and globular clusters. Some of these clusters orbit tens of thousands of light years above or below the galactic plane, far from the dense regions of the spiral arms. They are fossils of the galaxy's early history, relics from its formation more than 10 billion years ago. If you include the halo, the Milky Way stretches not 100,000 light-years, but closer to 300,000, and even that is not the whole story. Farther still, extending well beyond the halo, lies something we cannot see directly, the dark matter halo. This invisible component outweighs the visible galaxy by a large margin, perhaps 5 or 10 times its mass. We detect it only by its gravitational effects, watching how stars and gas move faster than they should if only visible matter were present. The dark matter halo may extend more than 1 million light-years from the centre, overlapping with the region where the gravity of the Andromeda galaxy begins to dominate. If we include this invisible halo, then the Milky Way is not just 100,000 light-years wide. It is 1 million, a colossal presence whose true boundary fades into intergalactic space. The difficulty of mapping these edges is obvious. You cannot fly to the rim and look back. You cannot take a photograph from outside. Instead, astronomers rely on indirect evidence, star counts, globular cluster positions, the motions of satellite galaxies, the speed of stars in the outer disk. Each method stretches the ruler farther, extending the map outward, but each comes with uncertainty. The galaxy does not cooperate by ending cleanly. It fades, thins, and merges. Even within the disk, defining the edge is tricky. The number of stars declines as you move outward, but where exactly does it stop being the Milky Way and start being empty space? Some astronomers define the disk's edge at the point where the density of stars falls below a certain threshold. Others extend it to where gas clouds are still found. Still others use the orbits of stars as a guide. Different definitions give different answers. That's why you might hear the Milky Way described as 100,000 light-years across in one place, and 120,000, or even 150,000 in another. The truth is that it doesn't have a sharp edge. It fades. The halo complicates things even more. Globular clusters can orbit hundreds of thousands of light-years from the centre, but they are still bound to the galaxy. Streams of stars, remnants of smaller galaxies torn apart by the Milky Way's gravity, also trail far into space. These streams blur the line between what is inside and what is outside. The galaxy is constantly interacting with its surroundings, pulling in material, merging with dwarfs, sending stars adrift. Its edges are porous, always shifting. And then there is the dark matter halo, the most elusive boundary of all. Though we cannot see it, simulations suggest it is the largest part of the galaxy, a diffuse, invisible cloud that gives the Milky Way its mass and gravitational reach. Without it, the outer stars would not orbit as fast as they do. With it, the galaxy's true size may be 10 times larger than the visible disk. But where does the dark matter halo end? We do not know. Its density falls gradually, blending into the halos of neighbouring galaxies. In some sense, there may not be a clear end at all. The Milky Way and Andromeda are already overlapping in their invisible halos, linked long before they physically collide. For us living within the disk, these edges are invisible. When you look up at the night sky, you see the concentrated stars of the inner disk. You cannot see where they fade into the outskirts. You cannot see the faint halo stretching outward, much less the dark matter beyond. To us, the galaxy is a band of light. To astronomers, it is a layered system: disk, bulge, halo, and dark matter. To define its edge is to decide which layer counts. The practical importance of mapping the edges is clear. Knowing the full size of the Milky Way helps us understand how it compares to other galaxies, how much mass it contains, how it interacts with its neighbours. For example, measuring the mass of the Milky Way tells us whether it is heavier or lighter than Andromeda, which affects predictions of their future collision. It also tells us how many stars and planets might exist, how much gas is available for new star formation, and how long the galaxy will continue to evolve. But on a more personal level, the idea of edges challenges the way we think about boundaries in general. On Earth, we like clear lines, shores, walls, fences. In the cosmos, boundaries are soft, fuzzy, and often invisible. The Milky Way does not stop. It fades, thins, overlaps. Its edges are a matter of definition, not fact. To ask how far does it go is to ask where we choose to stop calling it ours and start calling it other. If you could drift outward from the solar system, crossing the disk toward the rim, you would not notice a moment when the Milky Way ended. Stars would become less common, more scattered. Gas clouds would thin out. After tens of thousands of light years, the spiral arms would fade behind you. Keep going, and eventually you'd be surrounded by only a few stars, with the galaxy behind you as a glowing disk in the distance. Even then, you'd still be inside the halo, still bound by its gravity. To leave the Milky Way entirely, you would have to travel hundreds of thousands of light years farther than any light from Earth has yet reached. And even then, you would not be in empty space for long. The local group, our cosmic neighbourhood, is filled with dwarf galaxies, streams of stars, and the looming presence of Andromeda. The edges of the Milky Way blend into the beginnings of other systems. Galaxies are not isolated islands. They are members of larger structures, woven into the cosmic web. To define the Milky Way's edge is to draw an artificial line in a universe that resists such lines. Still, it helps to have numbers, even if they are approximate. Saying the Milky Way is 100,000 light-years across gives us a handle, a way to picture its scale. Saying its halo stretches 300,000 light-years helps us compare it to neighbours. Saying its dark matter extends 1,000,000 light-years places it in context with Andromeda. Each figure is a way of pointing to the immensity, even if none of them captures the whole truth. So how far does the Milky Way really go? Farther than we can see? Farther than we can easily define? Farther than the words themselves can capture? It extends through the disk you see in the night sky, through the halo you cannot see, through the dark matter you can only infer, blending outward into the larger universe. To live inside it is to live inside something whose edges are never truly reached. And as we trace those edges, the next question naturally arises. How many stars are contained within them? If the Milky Way stretches so far, what does that mean for the number of suns, the number of possible worlds, the number of lights that fill our galactic home? When you stand outside on a clear night, far from city lights, the stars you see overhead might feel like too many to number. Thousands shimmer across the dome of the sky, some bright, some faint, some clustered together in hazy bands. It seems impossible to count them all, and indeed for most of human history, that impossibility became a symbol. Stars were the very definition of uncountable, invoked in myths, in sacred texts, in metaphors of infinity. Yet what we see with our eyes is only the faintest surface of the Milky Way's true population. For every star visible to the naked eye, there are millions more too faint or too far to see. Telescopes reveal layer after layer, filling the galaxy with points of light until even instruments can no longer distinguish them individually. The question then becomes not whether the Milky Way has countless stars, but how many countless actually means. Astronomers have tried for centuries to pin down a number. The answers have shifted as methods improved, but the truth remains staggering. Our galaxy contains hundreds of billions of stars. The most common figure quoted today is around 100 to 400 billion. That wide range hints at the difficulty of the task. Counting stars in a galaxy is nothing like counting people in a city. You can't take a census of every individual. Instead, astronomers estimate by measuring light, mass, and models of stellar populations. They calculate how much total light the Milky Way produces, then divide by the average brightness of stars. Or they measure the total mass of the galaxy, subtract the contribution of gas and dark matter, and estimate how many stars would fit the remainder. Each method has uncertainties, and so the numbers vary, but whether the true count is closer to 100 billion or 400 billion, the scale is almost beyond comprehension. Imagine lining up 100 billion stars. If you counted one star every second, without pause, it would take you over 3,000 years to finish, and even then you'd still be missing some. The galaxy is so large and stars so numerous that the human mind struggles to hold the total. The stars themselves are not all alike. Some are small, cool red dwarfs, faint and long-lived, making up the majority of the galaxy's population. Others are hot, bright blue giants, burning furiously and dying young. Some are like the sun, medium in mass and temperature, steady for billions of years. The mix of these types influences how astronomers estimate totals. Because red dwarfs are faint, they are easy to miss, yet they may account for most of the stars in the Milky Way. Our census is incomplete, biased toward the bright and obvious. Beyond individual stars there are clusters. Globular clusters, ancient and spherical, contain hundreds of thousands of stars packed tightly together. Open clusters, younger and looser, scatter their stars across the arms. Each cluster is like a miniature galaxy in itself, a population bound together for a time before dispersing. These collections complicate the count, but they also enrich it, showing that stars are not isolated but part of larger families. And then there are stars that no longer shine. White dwarfs, neutron stars, and black holes are remnants of earlier generations. They're not luminous, so they are not easily included in the total, yet they remain part of the galaxy's population. In some ways, the Milky Way is a cemetery as well as a nursery, filled with the remnants of stars that lived and died billions of years ago. To count only the shining stars is to count only the living, not the full history. The number of stars also raises questions about planets. If the galaxy has 100 billion stars, and if most of them have planets, then the number of worlds must be staggering. Estimates suggest that there may be more planets than stars in the Milky Way, trillions of them, orbiting quietly, unseen from Earth. Among them, some are rocky like ours, some are gas giants, some are icy. Some may orbit in zones where liquid water is possible. Every star you see may host entire solar systems of its own, each with its own story unfolding. The realization that the Milky Way contains so many stars was not immediate. In the early days of telescopes, astronomers could only say that the number was far greater than the eye could perceive. William Herschel, counting stars through his giant telescope, saw numbers increase dramatically, but still underestimated the total because of dust and distance. It took modern instruments, space telescopes, and surveys across multiple wavelengths to push the count into the hundreds of billions. Even now, the uncertainty remains large, a sign of the challenge of studying something from within. Yet, while the exact number may be uncertain, the scale is clear. The Milky Way is not a small gathering of stars. It is a colossal city of suns, each one a blazing nuclear furnace, each one a potential host for planets, each one a part of the galaxy's overall life. To think of 100 billion stars is to think of 100 billion opportunities for worlds, for stories, for histories beyond our own. For perspective, consider this. If you held out your hand at arm's length and looked at a patch of sky the size of your fingernail, it would contain thousands of stars within the Milky Way. Each tiny fraction of the sky is crowded, even if it looks empty. The density is invisible to us because the stars are faint, but telescopes reveal them. Every point of darkness conceals more light, hidden by distance or dust. The galaxy is not sparse, it is overflowing, and of course, stars are not evenly distributed. They crowd in the spiral arms, where gas and dust create new generations. They thin out in the outskirts, where the disk fades into halo. They swarm in the bulge near the centre, packed so tightly that their light blends into a glow. Each region of the Milky Way has its own character, its own population density, its own balance of ages and types. To speak of 100 billion stars is to average across this variety, to compress the complexity into a single figure. The challenge of comprehending the number also changes the way we think about our own star, the Sun. It is one among billions, ordinary in most respects, and yet, to us, it is everything. It powers life, drives weather, marks time. From a galactic perspective, the Sun is just another yellow star, faint and unremarkable. From Earth, it is unique. This duality, the ordinary and the extraordinary, reminds us that every star in the Milky Way may be ordinary to the galaxy, but extraordinary to those who live around it. So, when we say the Milky Way has 100 billion stars, or 200 billion, or perhaps 400 billion, we're not giving a precise number, we're expressing immensity. The count is less about accuracy and more about scale. It tells us that the galaxy is filled beyond imagination, that the faint band of light is not mist but multitudes, that the stars visible to our eyes are only the tiniest sample of what surrounds us. And the presence of so many stars naturally leads to further questions. If each star has planets, and if some planets may have conditions for life, then what might be out there? How many civilizations could the galaxy contain? How many other beings might be looking up at their own skies, counting their own stars, wondering about their own Milky Way? The number of stars becomes not only a matter of astronomy, but of possibility, of speculation about life beyond Earth. And yet, before we leap too far ahead, it is worth lingering on what these numbers already tell us. The Milky Way is not a sparse system of a few scattered suns. It is a vibrant, crowded, dynamic population of hundreds of billions of stars. To live inside it is to be surrounded by more suns than you can ever see, more than you can ever imagine, each one a story unfolding in its own time. When we think about the Milky Way, it's natural to picture stars first. Billions of suns scattered across spiral arms, glowing nebulae, clusters, the bright bands stretched across the sky. These are the visible parts, the parts that photographs and telescopes can capture. But as striking as they are, they make up only a small fraction of what the galaxy truly is. The bulk of the Milky Way is not luminous. It does not shine, does not glow, does not scatter light. It is dark matter, an invisible component whose presence we know only by the way it tugs on the things we can see. The idea that most of the galaxy is invisible emerged slowly, almost reluctantly. In the early 20th century, astronomers measured how stars orbit in galaxies, including our own. What they expected was simple. The farther a star is from the centre, the slower it should move, just as planets farther from the Sun orbit more slowly. This is a basic consequence of gravity. But when astronomers made precise measurements, they found something surprising. Stars on the outer edges of galaxies, including the Milky Way, were not slowing down as expected. They were moving too fast, as if extra gravity were pulling on them. The only explanation was that there must be far more mass in the galaxy than what was visible. This hidden mass was not shining like stars, nor glowing like gas, nor radiating like hot plasma. It was invisible, detectable only by its gravitational pull. Astronomers named it dark matter, not because they knew what it was, but because they knew it was not luminous. It was a placeholder for an unknown reality, a way of admitting that galaxies weighed more than their visible parts suggested. Over time, evidence for dark matter grew. Not only do stars in the outer disk move faster than they should, but clusters of galaxies are also held together by unseen mass. Gravitational lensing, the bending of light by gravity, shows that invisible matter warps the paths of photons from distant galaxies. Everywhere astronomers looked, they saw the signature of extra gravity. The conclusion was inescapable. Most of the universe's matter is dark, not bright. In the Milky Way, this dark matter forms a vast halo surrounding the visible galaxy. If you could see it directly, it would extend far beyond the spiral arms, reaching hundreds of thousands, even 1,000,000 light-years from the centre. The stars, the nebulae, the bright core, all of it would be just a small glowing disk embedded in a much larger invisible cloud. This halo contains perhaps 5 times more mass than the visible galaxy. In other words, when you think of the Milky Way, most of what you're thinking of is something you cannot see. What is dark matter? That remains one of the greatest mysteries in physics. It is not made of ordinary atoms, because if it were, it would interact with light and be visible. It does not emit or absorb electromagnetic radiation. It interacts mainly through gravity, shaping the motions of stars and galaxies, but otherwise remaining elusive. Physicists have proposed many candidates, weakly interacting massive particles, axions, sterile neutrinos, but none has been detected directly. We know dark matter must be there. We do not yet know what it is. In the context of the Milky Way, the dark matter halo plays several roles. First, it provides the mass needed to hold the galaxy together. Without it, the outer stars would fly off into space, unable to remain bound. The spiral arms would not persist, the disk would unravel. Second, the halo shapes the way the Milky Way interacts with its neighbours. The gravitational field of the halo extends outward, pulling on dwarf galaxies, bending their paths, even consuming some of them. The streams of stars seen in the halo are remnants of these encounters, traces of smaller galaxies torn apart and absorbed. The halo also raises questions about the galaxy's origins. Simulations of cosmic structure show that dark matter clumped first in the early universe, forming scaffolds into which gas fell, cooled, and formed stars. In that sense, the Milky Way exists because of its halo. Without dark matter, galaxies like ours might never have formed at all. The invisible bulk is not an add-on, but the foundation, the framework within which everything else took shape. Despite its importance, the halo is nearly impossible to imagine. It has no sharp edge. Its density decreases gradually with distance, blending into the larger cosmic web. You would not feel it if you travelled through it. It does not block light or cast shadows. And yet, if you removed it, the Milky Way would fall apart. It is both intangible and essential, unseen but decisive. Astronomers map the halo by studying the motions of stars and clusters in its outskirts. Some stars orbit hundreds of thousands of light-years from the centre, their paths shaped by the halo's gravity. By measuring their speeds, astronomers infer the amount of dark matter pulling on them. Satellite galaxies also provide clues. The motions of the Magellanic Clouds, the Sagittarius Dwarf and other companions are influenced by the Milky Way's halo, allowing estimates of its extent and mass. These indirect measurements build a picture of a galaxy far larger than the glowing disk suggests. For us on Earth, living inside the halo, the experience is subtle. We do not see it, do not touch it, do not notice it in daily life. But every orbit of the Sun, every curve of the spiral arms, every motion of the galaxy's neighbours is shaped by it. We are immersed in an invisible ocean, drifting in currents we cannot sense directly. The stars above us are only the surface. The bulk lies beneath, unseen. And this realization changes how we think about scale. Earlier, when we spoke of the Milky Way being 100,000 light-years across, that was only the luminous part. With the halo included, the true size stretches 10 times farther. Suddenly the galaxy is not just a flat spiral, but a vast sphere. Its arms a glowing core within a larger invisible body. To imagine it is to imagine a lantern glowing inside a cloud, the light marking only the inner region, while the mass extends much farther. The presence of dark matter also shapes our future. The halo overlaps with that of the Andromeda Galaxy, meaning the two systems are already gravitationally connected. In billions of years, their visible disks will collide, but in a sense their halos are already merging. The invisible bulk links them long before their stars intertwine. The fate of the Milky Way is written not only in its stars but in its dark matter, the unseen weight that guides its path. And while dark matter remains mysterious, it also offers reassurance. It means the galaxy is more massive than it appears, more stable, more enduring. It means the motions of stars, the persistence of spiral arms, the binding of clusters all have a hidden foundation. We live not in a fragile structure, but in one rooted in invisible strength. The halo may be unknown, but it is also the reason the Milky Way has lasted billions of years and will last billions more. To think about it as a whole, the Milky Way is like an iceberg. The glowing stars and nebulae are the tip, the part we can see, floating above the surface. The dark matter halo is the bulk beneath, unseen but much larger. The difference is that while an iceberg hides its mass underwater, the galaxy hides its mass in a medium we cannot detect with our senses at all. It is there, shaping everything, even though it leaves no trace of light. If the Milky Way's bulk is dark and invisible, how does it compare to its neighbours? What happens when galaxies like ours, with their luminous disks and dark halos, meet and merge? When we imagine the Milky Way, it's natural to picture the spiral arms first, curling gracefully around a glowing centre, filled with stars and gas. But that isn't the whole galaxy. Surrounding the disk, above and below, extending far beyond the arms, is a vast, diffuse region called the halo. Unlike the bright disk, the halo is quiet and dim, a place of scattered stars, ancient clusters, and long, tenuous streams of matter. It is not where the galaxy's crowds gather. It is where the loners live. The halo is both simple and strange. Simple, because it lacks the dramatic structures of the spiral arms. No glowing nebulae, no bustling lanes of starbirth. Strange, because it contains objects that are among the oldest in the galaxy, remnants of a time before the Milky Way as we know it existed. If the spiral arms are the busy neighbourhoods of a modern city, the halo is the countryside filled with ruins, monuments, and echoes of the past. One of the most striking features of the halo are globular clusters. These are spherical groups of stars tightly packed, containing hundreds of thousands, sometimes millions, bound together by gravity into compact systems. Unlike open clusters in the spiral arms, which disperse after a few 100 million years, globular clusters endure for billions. They are ancient, nearly as old as the galaxy itself, fossils from its earliest era. Some may even predate the Milky Way, having been captured from smaller galaxies that merged into ours long ago. Globular clusters orbit the galactic centre and the halo, following elongated paths that take them high above and far below the disk. To see one through a telescope is to glimpse a glittering sphere, stars crowded so tightly in the core that they blur together. They are beautiful, but they are also clues. Their ages tell us when the first stars formed. Their positions trace the shape of the halo. Their compositions reveal chemical histories different from the younger stars of the disk. They are like archives, holding records from the dawn of the galaxy. Scattered among the clusters are individual stars wandering the halo. These stars are often old and metal-poor, meaning they formed before heavier elements were abundant. Their orbits are not the neat circular paths of disk stars. Instead, they are tilted, eccentric, plunging in and out of the galactic plane. Some may have been born in the Milky Way's earliest days. Others may have been stripped from dwarf galaxies consumed by the Milky Way's gravity. Together, they form a population that is sparse but revealing. Each one is a survivor, a traveller in the galaxy's outskirts. Even more mysterious are the stellar streams. These are long, thin trails of stars stretched across the halo, remnants of smaller galaxies or clusters that were torn apart by tidal forces. As the Milky Way pulled them in, their stars were scattered along their orbits, leaving faint ribbons that wrap around the galaxy. Dozens of these streams have been discovered, some stretching tens of thousands of light years. They're evidence that the halo is not just empty space, but a dynamic region, where the Milky Way's history of cannibalism is written in the paths of shredded companions. The halo itself extends far beyond what we can easily map. Stars and clusters in the halo can be found hundreds of thousands of light years from the galactic centre, much farther than the disk's edge. In fact, the halo may reach a third of the way to Andromeda, blending into the surrounding intergalactic medium, but the density of stars drops rapidly. The farther you go, the lonelier it becomes. The spiral arms fade into memory, the clusters thin out, and the darkness grows. Living in the halo, if such a thing were possible, would feel utterly different from living in the disk. In our solar neighbourhood, the nearest star is over 4 light-years away, a distance that already feels enormous. In the halo, stars are far more widely spaced, separated by vast stretches of emptiness. The night sky from such a vantage point would be strange, darker, with fewer stars close by, but with the Milky Way itself visible as a glowing disk in the distance. You would not be inside the crowd. You would be looking back at it, seeing the galaxy as an object against the black. In a way, the halo gives us a rare gift, perspective. From within the disk, we cannot see the Milky Way's full form, but if you could drift far enough into the halo, the galaxy would appear whole, a spiral shining across the void. It is in the halo that the Milky Way becomes visible as a single structure, not just as a band of light overhead. The halo is remote, but it provides the view we crave. For astronomers, the halo is crucial because it records the galaxy's history. Every globular cluster, every stream, every wandering star is a piece of the Milky Way story. They tell us when the first stars formed, which smaller galaxies were absorbed, how the Milky Way grew over time. By studying the halo, we reconstruct the past, peeling back billions of years of cosmic evolution. It is less glamorous than the star-forming arms, but in some ways it is more profound. The halo remembers what the disk has forgotten. The halo is also the region where the Milky Way meets its environment. Satellite galaxies orbit within it, dwarf companions like the Magellanic Clouds, the Sagittarius Dwarf, and many others. Some are intact, others are being consumed, their stars already stretched into streams. The halo is where the galaxy interacts with neighbours, where boundaries blur, where gravity pulls material in and out. It is the frontier of the Milky Way, a place of contact as well as solitude. And though the halo is vast, it is also fragile in our imagination. We cannot see it with the naked eye. We cannot sense it directly. To most people, the Milky Way ends with a band of light overhead. The halo is invisible, known only through telescopes and measurements. Yet without it, the galaxy would not be complete. It is the quiet frame around the bright painting, the wide field around the crowded city, the space that holds the whole together. Thinking about the halo also changes the way we think about ourselves. We live in the disk, but we are bound to the halo. Its gravity holds us, its history shaped us, its streams passed through us. The sun and its planets are not isolated. They are part of a larger structure, one that stretches far beyond the stars we can see. To realise this is to realise that our home is bigger, older, and more complex than we imagined. The Milky Way is not alone. Though it dominates its corner of the universe with hundreds of billions of stars, a massive halo of dark matter, and spiral arms sweeping across 100,000 light-years, it is surrounded by smaller companions. These are dwarf galaxies, faint satellites orbiting our own, each with its own collection of stars, gas and history. Some are nearly invisible, so dim that they were discovered only recently with deep sky surveys. Others, like the Magellanic Clouds, have been known since ancient times, visible even to the unaided eye from southern latitudes. Together they remind us that the Milky Way is part of a family, not an isolated island in space. The large and small Magellanic Clouds are the most famous of these companions. To observers in the southern hemisphere, they appear as hazy patches, 2 irregularly shaped smudges near the bright band of the Milky Way. For centuries, sailors used them as guides while crossing the oceans. Indigenous peoples of the southern hemisphere wove them into stories and calendars. To modern astronomy, they are dwarf galaxies in their own right, orbiting and interacting with the Milky Way. The large Magellanic Cloud contains about 30 billion stars, the small Magellanic Cloud about 3 billion, tiny compared to the Milky Way, yet substantial on their own. These clouds are not passive companions. They are dynamic, distorted by the Milky Way's gravity and in turn influencing it. Streams of gas connect them, forming a bridge that testifies to their ongoing interaction. A vast ribbon of hydrogen, the Magellanic Stream, stretches across the sky, stripped from the clouds as they orbit. These are signs of a relationship not of quiet orbit, but of exchange and disruption. In billions of years, the clouds may be fully absorbed, their stars scattered into the Milky Way's halo, their identity erased but their substance preserved. Beyond the Magellanic Clouds lie dozens of smaller dwarfs. Some, like the Sagittarius dwarf galaxy, are already being consumed. The Sagittarius dwarf orbits close to the Milky Way and has been torn apart over billions of years, leaving long streams of stars that wrap around the galaxy. These streams weave through the halo, silent traces of a companion's destruction. Others, like the Fornax dwarf or the Sculptor dwarf, orbit at greater distances, faint and tenuous, with only a few million stars. The faintest of these companions are almost invisible. Called ultra-faint dwarfs, they contain only a few thousand stars scattered across a wide area. They are so dim that they were unknown until the 21st century, discovered in surveys like the Sloan Digital Sky Survey, and later confirmed with more sensitive telescopes. These dwarfs are relics of the early universe, fragile and easily disrupted, yet still orbiting within the Milky Way's dark matter halo. Each one is a reminder that even in the galaxy's shadows, faint structures persist. The story of these companions is not one of static existence, but of constant change. Some are stable, orbiting quietly. Others are stretched, shredded, or swallowed, their stars pulled into the halo. The Milky Way grows by consuming them, adding their mass, their stars, their clusters. The halo is filled with the remains of past mergers, stellar streams marking the paths of galaxies long gone. To look at the dwarf galaxies is to see the Milky Way's appetite in action, the ongoing process by which large galaxies are built from smaller ones. For astronomers, studying these companions is crucial. They provide insights into dark matter, because their motions reveal how much unseen mass surrounds them. They tell us about the early stages of galaxy formation, since many are ancient and chemically simple, fossils of the first star-forming systems. They also show us the future, because the Milky Way's interaction with them foreshadows its eventual merger with Andromeda. The process of galactic growth is written in these satellites, visible on smaller scales before playing out on larger ones. From Earth, though, the experience is different. The Magellanic Clouds are visible to the naked eye from the southern latitudes, quiet patches of light that look almost like detached fragments of the Milky Way itself. To see them is to be reminded that the galaxy is not solitary, that companions drift nearby. The fainter dwarfs require telescopes, and even then they appear as diffuse smudges, barely distinguishable from the background. They do not announce themselves with grandeur. They whisper their existence, subtle and fragile. And yet, fragile though they are, their presence changes the way we think about the Milky Way. We are not an island, but part of a group. Our galaxy is orbited by dozens of smaller systems, and together with Andromeda and Triangulum, we form the local group, a small cluster of galaxies bound together. Within this group, the Milky Way is one of the giants, but its companions are part of its story. They orbit, they merge, they leave trails of stars in our sky. They're part of our identity, even as they lose their own. Think of the scale of it. A dwarf galaxy with a few million stars may seem tiny compared to 100 billion in the Milky Way, but from a human perspective, even a million stars is vast. Each one could host planets, some of which might resemble Earth. Entire histories could unfold there, unnoticed by us, hidden in faint smudges at the edge of visibility. The fact that they are small compared to the Milky Way does not mean they are small compared to us. To us, they are still beyond imagination. The interactions between the Milky Way and its satellites also shape the galaxy itself. Streams of stars from disrupted dwarfs add to the halo. Globular clusters may be donated by companions, captured during mergers. Gas pulled from satellites fuels star formation in the disk. The spiral arms may even be influenced by the pull of the Magellanic Clouds. In subtle ways, the companions leave fingerprints on the Milky Way structure, reminders that galaxies do not evolve in isolation. And when we step back, the picture becomes even larger. The Milky Way's satellites are not unique. Andromeda has its own companions, dozens of dwarfs orbiting it. Other galaxies in the universe are surrounded by swarms of smaller systems. This seems to be a rule of cosmic structure. Big galaxies come with little ones. They orbit, they merge, they scatter, they sustain the process of growth and change. Our galaxy is simply one example of a universal pattern. Still, there is something intimate about thinking of the Milky Way's companions. They are not distant galaxies billions of light years away. They are here, in our neighbourhood, part of our system. Some are close enough that their stars overlap with ours in the sky, indistinguishable without careful study. Some are being pulled apart even now, their substance blending into ours. They are neighbours in the truest sense, close enough to influence, close enough to touch. And as we consider these companions, the thought arises of what happens when galaxies interact on even larger scales. If dwarf galaxies can be consumed, what happens when two giants like the Milky Way and Andromeda meet? When you look up at the night sky, the stars appear fixed, steady, eternal. Constellations seem unchanging, as if they have always been and always will be. But on the scale of galaxies, stillness is an illusion. Galaxies move, they orbit, drift, pull, and collide. The Milky Way itself is no exception. It carries the scars of past collisions, and it is heading toward a future shaped by one of the most dramatic encounters imaginable. Collisions between galaxies are not rare. In fact, they are central to how galaxies grow. Small galaxies merge into larger ones, contributing their stars, gas, and dark matter. The Milky Way, with its halo filled with streams of stars and disrupted companions, is evidence of this process. Every stream is the ghost of a past merger, the remains of a smaller system consumed by our galaxy's gravity. Even the globular clusters scattered in the halo may once have belonged to dwarves that no longer exist as independent systems. One clear example is the Sagittarius dwarf galaxy. Today it is being torn apart, stretched into long arcs that wrap around the Milky Way. Its stars are spread thin, creating tidal streams visible across the sky. This is a collision in progress, slow but relentless. Over time, the Sagittarius dwarf will disappear, its stars absorbed into the larger whole. The same fate has befallen many others before it, leaving behind the faint signatures astronomers now trace. The halo of the Milky Way is, in part, a graveyard of galaxies. Their individual identities erased, but their substance still present. But collisions are not only about the past. The Milky Way is currently on a path toward Andromeda, the nearest giant spiral galaxy. Located about 2.5 million light-years away, Andromeda is moving toward us at roughly 110 kilometers per second. That may sound slow compared to the speed of light, but over millions of years, it is decisive. In about 4 to 5 billion years, the Milky Way and Andromeda will meet. Their halos are already overlapping. Their stars, gas, and dark matter are already tugging on each other. The collision has, in a sense, already begun. What will that encounter look like? It's natural to imagine galaxies smashing together violently, stars colliding, worlds destroyed. But the reality is subtler. Galaxies are mostly empty space. Stars are so far apart that direct collisions are rare, even in galactic mergers. Instead, what happens is gravitational. The galaxies will pass through each other, their shapes distorted, spiral arms stretched and twisted, stars flung into new orbits. Clouds of gas will collide, triggering bursts of star formation. Over billions of years, the two galaxies will dance, merging, separating, merging again, until they settle into a new form. That new form will likely be an elliptical galaxy, a large, smooth structure without the spiral arms we see today. Astronomers have even given it a name, Milky, the combined galaxy that will result from the merger. Its stars will include ours, carried along in the flow, orbiting the new centre of mass. The Sun itself may find its orbit altered, perhaps thrown farther from the centre, perhaps pulled inward. Earth, if it still exists then, will see a night sky transformed. Instead of a faint smudge of Andromeda in the distance, the galaxy will dominate the heavens, first as a growing blur, then as a sprawling web of stars stretching across the entire sky. From a human timescale, this future is impossibly distant, but in cosmic terms, it is near. The Sun is about halfway through its life, with 5 billion years of steady burning left. That means the Milky Way Andromeda collision will happen before the Sun becomes a red giant. If Earth survives until then, the collision will be part of our planet's distant story. The skies will tell of galaxies in motion, a reminder that even structures as vast as these are not fixed but evolving. Collisions like this are common across the universe. Telescopes capture images of interacting galaxies, their shapes distorted into arcs, bridges and tails. Some show spirals tearing at each other, others reveal giant ellipticals formed by past mergers. In these images we see the Milky Way's future. Our galaxy is not unique in its destiny. It is part of a cosmic cycle, where galaxies grow by merging, where structures change form, where the universe itself evolves. The thought of such collisions might seem unsettling, but they are also creative. Gas clouds compressed in mergers ignite new generations of stars. Old stars find new orbits, mixing populations, blending histories. Black holes at galactic centres may merge, creating gravitational waves that ripple across the cosmos. The result is not destruction, but transformation. Galaxies are not fragile. They are dynamic, reshaping themselves over billions of years. And even on smaller scales, collisions matter. The Magellanic Clouds, orbiting nearby, are already influencing the Milky Way, pulling at its disk, fueling streams of gas that may spark future star formation. The Sagittarius dwarf is leaving streams that enrich the halo. Every interaction, large or small, adds to the Milky Way's character. The galaxy we see today is the product of countless past collisions, and the galaxy of the future will be the product of countless more. From Earth, these processes are invisible in the moment. The stars we see tonight will not shift perceptibly in our lifetimes. The constellations will not dissolve before our eyes. But if we could watch the Milky Way over millions of years, the changes would be obvious. Arms would stretch, companions would merge, the galaxy would alter shape. The slow dance is always underway, even if we cannot perceive it. Thinking of these collisions also changes how we think about permanence. Nothing in the universe is fixed forever. Galaxies grow, merge, transform. The Milky Way as we know it is only one phase in a long story. Billions of years ago, it was smaller, less structured. Billions of years from now, it will be larger, different in shape, different in population. To live within it is to live inside a system always in motion, even if the motion is too slow for us to feel. And so, when we ask about the Milky Way's size, its stars, its halo, its companions, we must also ask about its future. The galaxy we describe today is not the galaxy of tomorrow. It is changing, shaped by interactions, by collisions past and future. Its fate is tied to Andromeda, to the local group, to the larger structures of the cosmos. To understand it is to see it not as a fixed object, but as a process, a story unfolding across time. In the midst of all this motion, all this growth and change, where exactly do we fit? For all the grandeur of the Milky Way, its sweeping spiral arms, its ancient halo, its invisible dark matter bulk, its restless history of collisions, our own place within it is surprisingly quiet. The solar system is not near the crowded core, where stars press close together, nor is it on the outermost edge. where the disk fades into sparsity. Instead, we live in what might be called a galactic suburb, a modest and unassuming neighbourhood in the Orion Arm, tucked between larger, more prominent spiral arms. This location is significant. It has shaped not only our view of the galaxy, but also perhaps our very existence. The Orion Arm is not one of the Milky Way's main highways. Those are the Perseus Arm and the Scutum Centaurus Arm, sweeping arcs where massive star formation blazes and young clusters crowd the lanes. The Orion Arm is more like a side road, a spur that branches between the larger arms. It is narrower, quieter, with fewer giant clusters and fewer bursts of activity. To live here is to live away from the brightest lights, in a more tranquil part of the City of Stars. From Earth, this placement affects everything we see. When we look towards Sagittarius in the summer sky, we are gazing inward toward the galactic centre, through thick lanes of stars and dust. That is why the Milky Way appears brighter in that direction. When we look toward Orion in the winter, we're gazing outward, toward the edge of the disk through thinner star fields. That is why the band appears fainter there. Our view of the Milky Way is a direct consequence of where we sit inside it, half a galactic radius from the core, orbiting calmly within the Orion Arm. This suburb is not empty. The Orion Arm hosts its own regions of star formation, including the famous Orion Nebula, visible to the naked eye as a faint smudge in Orion's sword. It is a nursery of new stars, a miniature version of the grander star factories in the major arms. Other nebulae, like the Eagle Nebula, with its towering pillars of creation, also lie nearby, sculpting new generations of suns. Our neighbourhood has its own points of interest, its own stories unfolding, even if it is less dramatic than the galaxy's downtown. Being in a quieter suburb has advantages. The galactic centre, while dazzling, is a chaotic place. Stars crowd so densely that interactions are frequent, radiation levels are high, and the supermassive black hole dominates the dynamics. The outer rim, while calmer, offers fewer resources, with less gas and dust for new star formation. Our location offers a balance, stable, not too crowded, not too barren. It is the kind of environment where a solar system can form, where planets can orbit undisturbed, where life can emerge and persist. Astronomers sometimes call this region the galactic habitable zone. It's a loose idea, not as specific as the habitable zone around a star where liquid water can exist on a planet's surface, but the analogy works. Too close to the centre, and the risks are higher. Supernovae, gamma-ray bursts, gravitational chaos. Too far out, and there may not be enough heavy elements for rocky planets to form. Somewhere in between lies a sweet spot. The Sun's position, about 26,000 light-years from the centre, seems to fall within that zone. It is a cosmic compromise, not too hot, not too cold, not too busy, not too empty. This quietness has consequences for how we experience the sky. In the galactic centre, the night would be ablaze, with dozens of bright stars visible where we see only a few. In the outer rim, the sky would be thinner, emptier, darker. From Earth, the sky is rich enough to inspire wonder, but not so overwhelming as to blind us. The constellations are visible against the dark, their patterns clear. The Milky Way's band is prominent but not overpowering. Our suburb provides a view both grand and gentle, and in this view, we see only a fraction of what surrounds us. The Sun is one of hundreds of billions of stars in the galaxy, yet from Earth we can see only a few thousand at most. Our neighbourhood hides the immensity. The Orion Arm stretches thousands of light-years, containing clusters, nebulae, associations of stars, yet we experience it as a familiar night sky dotted with constellations. The reality is far larger, but from our suburban vantage, it feels intimate. Our orbit around the galaxy also reflects this stability. The Sun circles the galactic centre every 225 million years, moving at nearly 828,000 kilometres per hour. It has completed only about 20 orbits in its 4.6 billion year lifetime. Each orbit is a galactic year, far beyond human time. In that span, continents drift, species rise and fall, civilizations appear and vanish, yet the sun continues its steady path. We are passengers in a long, slow journey, one we can barely perceive. This suburb is not immune to change. Over time, the sun passes in and out of different regions of the Orion Arm. Sometimes it drifts closer to active star-forming regions, sometimes farther away. Some researchers have speculated that these passages could influence Earth's history, perhaps through changes in radiation or nearby supernovae. Others argue the effects are minor. Either way, our orbit carries us through a varied landscape, even within this quieter neighbourhood. And our suburb is not static. The Orion Arm itself is not a fixed structure, but part of the galaxy's spiral pattern, shaped by density waves, moving and evolving over millions of years. The stars within it, including the Sun, do not remain fixed. They drift, orbiting the centre, migrating over time. Our neighbourhood today is not the neighbourhood of yesterday, and it will not be the neighbourhood of tomorrow. Yet the pace of change is slow, unfolding over spans far beyond a human lifetime. Thinking of our location in the galaxy invites reflection. On Earth, we often speak of home as a country, a city, a street, a house. But from a galactic perspective, home includes an arm of stars, a position halfway to the centre, an orbit within a spiral disk. We are suburban dwellers in a cosmic city, living not in the bustling core or the lonely edge, but in the middle, in a region of balance. That placement has shaped everything, from the view of the night sky to the very possibility of our existence. It also frames how we imagine the galaxy as a whole. From here, we cannot see the spiral arms as structures. We see only the local stars, the nearby clusters, the glowing patches of nebulae. To us, the Milky Way is a band of light, not a grand spiral. To picture it as a whole, we must step outside, either with imagination or with the aid of telescopes studying other galaxies. Our place gives us perspective on the galaxy's immensity, but also limits our view. We are both inside and blind to its full form. Still, the quiet suburb offers what we need. It offers stability, space, and the conditions for life. It offers skies filled with stars, but not so crowded as to confuse or overwhelm. It offers a vantage point from which to look outward, not only at the galaxy, but at the universe beyond. From here, we discover the spiral arms, the galactic centre, the halo, the dark matter. From here, we learn that we live in a galaxy at all. If this is our view from within, limited, partial, shaped by our position, what would the Milky Way look like from outside? If we could step away, drift into the halo, or cross the void between galaxies, and look back at our home, what would we see? From within the Milky Way, our view is partial. We see only cross-sections, fragments, patches of light cut by lanes of dust. The spiral arms, the bulge, the halo, all of it is hidden by our position inside. To imagine the Milky Way as a whole, we must step outside in thought. We must drift beyond the disk, into the halo, into the emptiness between galaxies and look back. Only then can we picture the galaxy as it truly is. A great spiral, glowing against the darkness, one among billions scattered across the cosmic web. What would it look like from that vantage point? To begin, think of the familiar photographs of spiral galaxies taken by telescopes. The Andromeda Galaxy, the Whirlpool Galaxy, the Pinwheel Galaxy. Images that show sweeping arms of stars, delicate filigrees of dust, glowing patches of nebulae. The Milky Way would resemble these because we are one of them. It would be a flattened disk, about 100,000 light-years across, with a central bulge rising from its middle, wrapped in curving arms that spiral outward. Around it, a faint halo of stars and clusters would glow dimly, extending farther still. From a distance of several million light-years, the Milky Way would appear as a small patch of light. The central bulge would be bright, the spiral arms fainter, their patterns visible only with sensitive eyes or instruments. Closer in, at hundreds of thousands of light-years, the structure would sharpen. You would see the four main arms, the Perseus, Scutum Centaurus, Norma, and Sagittarius, curving outward like the limbs of a great whirlpool. Between them, smaller arms and spurs would thread their way, including the Orion arm, where our sun resides. From afar it would be invisible, too small to notice among the larger patterns. The colours would be subtle. Spiral arms glow blue where young massive stars cluster, lighting the gas around them. Redder regions would mark older populations, stars long past their prime. Pinkish patches of emission nebulae would shine where new stars are born, glowing with hydrogen excited by ultraviolet light. Dark lanes of dust would cut across the arms, silhouetted against the glow. The bulge would shine golden, filled with old stars packed tightly together. Around all of this, the halo would be faint, barely visible, containing globular clusters that sparkle like satellites around the main disk. The view would depend on your perspective. From above the disk, the Milky Way would look like a grand spiral, its arms stretching outward in symmetry and grace. From the side, it would appear thin and flat, with the bulge rising in the middle, a shape sometimes described as a fried egg galaxy. Yolk in the centre, white spreading outward. From the edge, the disk would narrow to a line, its thickness only a few thousand light-years compared to its length of 100,000. Against the black of space, the contrast would be striking. This imagined view is not mere fantasy. Astronomers use observations of other galaxies as mirrors. By studying spirals like Andromeda, the Whirlpool, or Triangulum, they infer what our galaxy must look like. Computer models, fed with data about stellar populations, gas distribution and motion, create simulated views from outside. In these images, the Milky Way is both familiar and extraordinary. Familiar because it resembles countless other spirals we've seen. Extraordinary because it is ours. From outside, the scale becomes more apparent. The sun, so central to us, is a tiny dot buried in one of the minor arms. Even the Orion arm itself is small, just a spur branching between larger arms. Our entire solar system is invisible, lost among billions of others. To pick it out would be impossible. From outside, we are part of the glow, indistinguishable from the rest. The Milky Way does not announce our presence. It is indifferent, vast, whole. And yet to see the Milky Way from outside would be breathtaking. Imagine floating far enough into space that the galaxy fills the view, its arms stretched across hundreds of thousands of light-years, its glow faint but steady. It would not be static. The spiral arms would rotate slowly, the disk turning once every few 100 million years. If you could speed up time, you would see the arms ripple, stars forming and fading, clusters drifting, gas clouds collapsing and dispersing. The galaxy would appear alive, dynamic, a vast organism in constant motion. The halo would add another dimension. Surrounding the disk, faint globular clusters would orbit like fireflies, some plunging through the disk, others drifting far above it. Stellar streams, remnants of consumed dwarfs, would loop and arc, faint ribbons stretching across the sky. The dark matter halo, invisible, would nonetheless shape everything, holding the galaxy together, extending far beyond what your eyes could see. The Milky Way would not end where the light fades. It would continue in gravity, unseen but felt. From outside you might also notice the companions. The Magellanic Clouds would appear as small, irregular smudges orbiting nearby, connected by streams of gas. Other dwarfs would dot the halo, faint and scattered, barely visible but still present, and beyond them you would see Andromeda, shining brighter than most stars in the background, its spiral arms spread wide, its disk tilted in perspective. The two galaxies, Milky Way and Andromeda, would appear as partners in a slow approach, their halos already overlapping, their future collision written in their proximity. It is striking to think that we cannot see our own galaxy this way. We live inside it, blind to its overall form. Every image you've seen of the Milky Way from outside is either an artist's impression or a model based on other galaxies. We can photograph distant spirals in exquisite detail, but not our own. Our perspective is limited, locked inside the disk. And yet, through observation, inference, and imagination, we can reconstruct the view. We can picture ourselves from the outside, even if we cannot go there. This exercise is more than aesthetic. To see the Milky Way from outside is to put ourselves in context. It reminds us that our place is small, that our solar system is just one speck among billions. It also reminds us of connection, that the galaxy we call home is part of a family of galaxies, part of larger structures, part of a universe filled with spirals and ellipticals and irregulars, each with their own stories. From outside, the Milky Way is one among many, no more or less remarkable than countless others. And yet, to us, it is singular, because it is where we live. If you could see it with your own eyes, floating far above, perhaps the most striking feeling would be one of belonging. The Milky Way is not an abstract diagram or a number in a textbook. It is a real object, vast and luminous, and you are inside it. Its arms curve around you, its gravity holds you, its stars surround you. To see it from outside would be to see your true home, not the street or the planet or the solar system, but the galaxy itself, whole and immense. If we can imagine the Milky Way from outside, how does it compare to other galaxies in the universe? Is it typical, average, unremarkable, or is it unusual in some way, larger, brighter, different? When we study the Milky Way, we're not only studying our home, we're also studying the universe. Every detail we uncover about the galaxy, its size, its stars, its dark matter, its companions, becomes a clue to the nature of galaxies everywhere. The Milky Way is one example out of billions, but it is the one we can know most intimately. By looking outward from inside, we glimpse the larger patterns of the cosmos. The first lesson the Milky Way gives us is about scale. To say it is 100,000 light-years across with hundreds of billions of stars is to admit that galaxies are vast beyond human comprehension, and then to realise that the Milky Way is only one of perhaps 2 trillion galaxies in the observable universe is to stretch that scale even further. The Milky Way tells us that immensity is normal. Our galaxy feels enormous, and it is, but in the universe it is not exceptional. It is one thread in a tapestry so large that even 100 billion stars become routine. The second lesson is about structure. The Milky Way shows us what galaxies are made of: disks, bulges, halos, clusters, and dark matter. By mapping our own, we build a template for understanding others. When we see spiral galaxies millions of light-years away, their arms glowing and their bulges bright, we recognise them because we live in one ourselves. The Milky Way tells us that galaxies are not random clouds of stars but organised systems shaped by gravity into repeating forms, spirals, ellipticals, irregulars. These are the categories that emerge from billions of years of evolution, and our home is one of the clearest examples. The third lesson is about time. In the halo, in the globular clusters, in the streams of stars from past mergers, the Milky Way preserves its history. It is not a static object, but a record of billions of years. By reading that record, astronomers learn how galaxies form and grow. They begin as clumps of gas and dark matter, form stars, merge with others, and evolve into larger systems. The Milky Way tells us that galaxies are not born in their current state. They are built over time, through processes of creation and destruction, growth and change. The fourth lesson is about connection. The Milky Way is not isolated. It has companions. It belongs to the local group, and it is part of the larger Virgo supercluster. Its future is tied to Andromeda, with which it will merge. Its present is shaped by dwarfs being consumed. Its past is written in the streams of stars from galaxies long gone. The Milky Way tells us that nothing in the universe stands alone. Every galaxy is linked to others, through gravity, through mergers, through the cosmic web that connects them all. The fifth lesson is about the unseen. Most of the Milky Way's mass is dark matter, invisible and mysterious. We cannot see it, but its pull shapes the galaxy, binds it, defines its extent. By recognizing this in our own galaxy, we recognize it everywhere. The Milky Way tells us that the universe is not what it seems, that most of its content is hidden. What we see, the stars, the nebulae, the glowing disks, are only a fraction of reality. The true universe is darker, stranger, deeper. The sixth lesson is about perspective. From inside the Milky Way, we cannot see its full form. We infer it by studying others. From outside, we would see it as one spiral among many. Both views remind us of our limits. The Milky Way tells us that perspective matters, that where we stand shapes what we know. We are both inside and outside, both participant and observer, both local and cosmic. The galaxy reflects the way the universe itself must be approached, with humility about what we can see and imagination for what we cannot. And perhaps the most profound lesson is about place. The Milky Way is our home, but it is also ordinary. There are galaxies larger, galaxies smaller, galaxies brighter, galaxies dimmer. To the universe, the Milky Way is not special, and yet, to us, it is everything. It is where the sun resides, where Earth orbits, where life has emerged, where we look up at the night sky and wonder. The Milky Way tells us that significance is relative. To the universe, we are one among many. To ourselves, we are unique. Both truths coexist, both meaningful in their own way. When we step back and look at the Milky Way as part of the whole, we begin to see the universe as a web of galaxies, each a city of stars, each with its own structure, its own history, its own future. Some are spirals like ours, others are smooth ellipticals, others are chaotic irregulars. Together they fill the cosmos with light and gravity, islands of matter in the vastness of space. The Milky Way is our island, the one we know best, but it is also one island among billions. This realization is not meant to make us feel small, though it often does. It is meant to make us feel connected. We are not outside the universe, observing it. We're inside, part of it, made of the same matter that forms the stars. The hydrogen in our bodies was forged in the Big Bang, the heavier elements in supernovae, scattered across the galaxy and gathered into the Sun and Earth. To say we live in the Milky Way is not to say we live next to it. It is to say we are of it, born from its substance, moving within its orbit. The Milky Way tells us that the universe is not separate from us. It is us. And so, when we ask, how big is the Milky Way really? We're also asking, how big is the universe? Because every detail of our galaxy reflects the larger whole. Its size tells us about the scale of galaxies. Its stars tell us about the abundance of suns. Its dark matter tells us about the hidden mass that fills the cosmos. Its mergers tell us about the evolution of structure. Its position in the local group tells us about the clustering of galaxies. To study one is to study all. The Milky Way is both particular and universal, local and cosmic. If you could stand outside, in the dark of intergalactic space, and look back, you would see the Milky Way shining as one spiral among many. It would not announce itself as special. It would not be brighter or larger than countless others. But to you, it would carry a weight no other could, because it is the galaxy that gave rise to you. And from that vantage, you might realize the final lesson. The Milky Way tells us that the universe is not only vast and ancient, but also personal. It is the backdrop of our existence, the stage on which our story unfolds. It is both infinite in scope and intimate in meaning. You've drifted with me through the galaxy, through its centre and its arms, through its outskirts and its companions. You've imagined its shape from outside, and you've considered its place among billions of galaxies across the universe. And now, as the story carries us back, it helps to pause and notice where we truly are. Not out in the halo, not hovering beyond the disk, but here, on a small planet orbiting an ordinary star in the Orion Arm. The Milky Way, with all its grandeur, is the backdrop of our nights. Yet most of the time, we live without thinking of it. We look at the sky and see a handful of familiar constellations. We note the moon's phases, the bright wanderings of Venus, Mars, Jupiter. Sometimes we notice the misty band overhead, the Milky Way itself, especially on a clear night far from lights. And then, after a glance, we look away. The everyday world takes our attention. The galaxy recedes into silence. But it is always there. Every night, even when clouds hide the stars or city lights dim them, the galaxy stretches overhead, encircling us. Every morning, when the sun rises and washes away the stars, it is still present, invisible in the blue, but surrounding us nonetheless. We are never outside of it. We are immersed in it, carried along by its gravity, part of its endless turning. Think of the orbit you are part of. The Earth circles the Sun once each year, the rhythm by which we measure time. The Sun, in turn, circles the galactic centre once every 225 million years. Tonight, as you sit or lie wherever you are, you're moving, fast beyond imagining, 828,000 kilometres every hour, yet it feels like stillness. The ground beneath you is steady, the night is calm, the sky is fixed. That is the paradox of scale. Our senses are tuned to small motions, not to the sweep of galaxies. But those motions are real, and you are part of them. When you look up, the stars you see are only the nearest neighbours, dots within a few hundred or thousand light years. They are the front porch of the galaxy. Behind them, hidden by distance and faintness, are billions more. And beyond those, in directions your eyes cannot reach, lie galaxies upon galaxies stretching outward in every direction. Yet in this moment, you see only a few points of light. That is enough. The immensity can fade into the background. What you need is what you see, the quiet of your sky tonight. It's easy, after speaking of billions and trillions, of light years and halos, to feel small, even insignificant. But scale works both ways. You may be one person in a vast galaxy, but the galaxy itself contains you. It holds you as surely as it holds the sun, the arms, the stars. You're not outside of it, not separate from it, but woven into it. The atoms in your body were forged in stars that lived and died long before Earth existed. The calcium in your bones, the iron in your blood, the oxygen you breathe, they are the products of stellar furnaces scattered into space and gathered here. You are the Milky Way made conscious, looking back upon itself. And so, as you return from this journey through arms and clusters, through black holes and halos, let yourself return also to the immediacy of your own night. Notice the air around you, the surface beneath you, the quiet sounds nearby. The galaxy is vast, but your place within it is here, in this moment, on this planet, under this sky. That is not smaller. It is just closer. The cosmic and the personal are not separate. They are two sides of the same story. If you are outside, look up again. See how the stars shine steady, how the Milky Way arches across the sky. If you're indoors, imagine it. Picture the band of light, the glow of countless stars. Picture the centre hidden in Sagittarius, the arms curling outward, the halo fading into darkness. Picture yourself within it, not apart from it. That is what tonight offers, a reminder that you belong to something vast, yet you live within it in a way that is intimate and immediate. And as we close, let the galaxy fade softly into the background. Let the numbers, hundreds of billions, millions of light years, become less pressing. Let the details, spiral arms, dark matter, clusters, drift like distant echoes. What remains is the simple truth that you are in the Milky Way tonight, as you were yesterday, as you will be tomorrow. The stars above are your neighbours, the galaxy is your home, and the universe, vast though it is not foreign. It is the place you already belong. Thank you for drifting through the galaxy with me tonight. If you found this journey soothing, you might like to let yourself return here again, whenever you want a quiet space to rest or to wonder. You can even share this with someone who might enjoy a calm night under the stars, and if you'd like to join me for more slow explorations, you can follow along so that each new story finds you wherever you are. For now, you don't need to hold on to the numbers, the distances, the billions of stars. You can let them dissolve, like the last traces of daylight fading into night. What matters is the calm that remains, the steady rhythm of your breath, the comfort of your place in this moment. The Milky Way will keep turning, the stars will keep shining, and you, here and now, can rest. Good night.